If the universe is infinite, how did we measure it? Have you ever looked up at the night sky and wondered, how far does it go? Billions of stars, billions of galaxies, stretching beyond what our eyes can see. But what if the universe doesn't just stretch far, it goes on forever? If the universe is infinite, how can humans even measure it? How can we make sense of distances so vast that light itself takes billions of years to travel them? In this video, we're going to explore the clever ways scientists measure the cosmos, from the light of distant galaxies to exploding stars and ripples left over from the Big Bang, uncovering how we can map a universe that might never end. Early attempts to measure the universe. You see, long before the hum of telescopes and the crackle of computers measuring galaxies billions of light years away, humans looked up at the night sky with wonder, curiosity, and an urgent desire to make sense of the vast expanse above. The universe, though incomprehensibly enormous by modern standards, was first approached with the tools of geometry, observation, and imagination. The earliest astronomers may have lacked the sophisticated instruments we take for granted today, but their insights laid the foundation for everything that followed. They were the first cartographers of the heavens, charting stars, tracking their movements, and daring to imagine the distance to the sun, the moon, and beyond. Among the earliest of these astronomical pioneers was Hipparchus of Nicaea, born around 190 BCE. Hipparchus is often considered the father of trigonometry and one of the greatest observational astronomers of antiquity. He lived in a world where the motions of the planets, stars, and sun were largely a mystery, governed more by myth and philosophy than by precise measurement. Yet, Hipparchus's brilliance lay in his insistence on systematically cataloguing the heavens. Using painstaking observations, he compiled the first known star catalogue, listing approximately 850 stars, recording their positions and brightnesses or magnitudes with remarkable accuracy. This catalogue was not merely an exercise in bookkeeping. It represented a revolutionary attempt to impose order on the apparent chaos of the night sky. By mapping star positions against the celestial sphere, Hipparchus could detect subtle movements of stars over time, most famously discovering the precession of the equinoxes, a slow wobble in Earth's rotational axis that shifts the orientation of the heavens over thousands of years. This discovery demonstrated that the cosmos was dynamic, not static, and that careful observation over time could reveal patterns invisible to the casual observer. Hipparchus's methods relied on simple yet profound geometric principles, measuring angles between stars with instruments like the astrolabe, applying basic trigonometry, and using the horizon as a reference. Through this, he laid the groundwork for later astronomers to begin considering not just the positions of stars, but their distances and scales, sowing the seeds of thinking about the universe as a measurable entity. While Hipparchus was focused on the stars themselves, Aristarchus of Samos, who lived slightly earlier, was one of the first to attempt measuring the distance to the sun and moon using pure geometry and careful observation. Around 270 BCE, Aristarchus devised an ingenious method based on the phases of the moon and the geometry of right triangles. Observing the moon when it was exactly half illuminated, he reasoned that the angle between the sun and moon from Earth must form a right triangle. By measuring this angle as accurately as possible, Aristarchus could then estimate the relative distances from Earth to the moon and the sun. Although his measurements were off by modern standards, the sun turned out to be much farther than he calculated. The conceptual breakthrough was enormous. For the first time, someone had tried to translate the celestial dance of bodies into measurable distances, moving beyond mere cataloguing of positions to understanding the spatial relationships of heavenly objects. Aristarchus's work demonstrated the power of geometry to make the invisible visible, to give numerical meaning to the abstract vastness of the sky. It was a method grounded not in myth or philosophy, but in observation, logic, and mathematics, the very tools that modern astronomy still relies on. alongside these individual visionaries, there were also early thinkers who focused on measuring the scale of the Earth itself, because understanding the Earth was essential for measuring the heavens. Eratosthenes of Cyrene, living in the 3rd century BCE, performed what might be the first truly scientific measurement of Earth's circumference. Eratosthenes knew that at noon on the summer solstice in Syene, modern Aswan, Egypt, the sun cast no shadow. It shone directly overhead in deep wells, illuminating the water without reflection. At the same moment in Alexandria, a city far to the north, he measured the angle of the sun's rays using a simple vertical stick, or gnomon, and found the shadow cast an angle of approximately 7 degrees, or 1/50th of a full circle. Using basic geometry, he reasoned that if 7 degrees of Earth's circle corresponded to the distance between Syene and Alexandria, then the full circumference of the Earth must be 50 times that distance. His calculation yielded an estimate remarkably close to the modern value, about 39,375 kilometers, only a few percent off from the actual 40,075 kilometers. This achievement was not merely a demonstration of cleverness. It proved that the size of the Earth could be determined using careful measurement and geometric reasoning, a principle that would later allow astronomers to measure distances to celestial objects by scaling their observations against Earth's dimensions. Eratosthenes' approach was profoundly scientific, relying on observation, mathematics, and logical deduction, and it illustrated a central principle. Even without leaving Earth, one could begin to measure the universe. Eratosthenes' work also emphasized a fundamental insight that would echo through the centuries. Measuring the heavens requires understanding the observer's position in space. Knowing the size of Earth allowed future astronomers to calculate distances to the Moon, the Sun, and eventually the planets with greater accuracy. The interplay between terrestrial measurement and celestial observation became a cornerstone of astronomy because the scale of human tools, sticks, gnomons, astrolabes, could be extended to the cosmos if the basic geometric relationships were understood. Hipparchus, Aristarchus, and Eratosthenes together represent the dawn of what we might call quantitative astronomy. Hipparchus's star catalogues established the positions and movements of celestial bodies with unprecedented accuracy. Aristarchus's geometric calculations reached out into the void to estimate distances to the Sun and Moon, and Eratosthenes' measurement of Earth provided a scale against which the cosmos could be gauged. Each built upon the insights of his predecessors, showing that observation, mathematics, and geometry could transform awe and wonder into numerical understanding. The tools they used were deceptively simple. Hipparchus relied on the astrolabe, a sophisticated instrument for measuring angles in the sky. Aristarchus relied on careful timing and angular measurements of lunar phases. Eratosthenes used a stick and shadows. Yet despite their simplicity, these tools enabled the first human attempts to measure the immeasurable, to give numbers to what once seemed boundless and chaotic. They also illustrate a deeper principle, that the universe, no matter how vast, can be approached scientifically through observation, reasoning, and the clever application of geometry. The efforts of these ancient astronomers also highlight the limitations of early measurement, which paradoxically helped drive further discovery. Aristarchus's estimate of the distance to the Sun was off by a factor of 20, revealing both the audacity and the challenge of measuring the cosmos. Hipparchus's star catalogues were limited by the precision of his instruments and the naked eye. Eratosthenes' measurement of Earth, while remarkably accurate, depended on assumptions about the location of Syene relative to Alexandria and the verticality of wells. Yet these imperfections were not failures. They were the first steps in a long chain of refinement that would stretch over 2 millennia, eventually leading to the precise measurements of stars, galaxies, and the universe itself that we enjoy today. The questions these pioneers asked were both simple and profound. How far is the Moon? How far is the Sun? How big is the Earth? How can we measure the heavens from our tiny position on a rotating sphere hurtling through space? These questions were the same ones that would drive every astronomer who came after them, from Ptolemy in the 2nd century CE to Copernicus in the 16th century, from Galileo with his telescopes to modern scientists using space probes and satellites. The methods they developed, observation, cataloging, geometric reasoning, were the first attempts to bring structure to the infinite, to take the immeasurable universe and make it tangible. Hipparchus, Aristarchus, and Eratosthenes also remind us that early astronomy was a blend of ingenuity, persistence, and careful measurement. Each relied on repeated observations, careful recording of data, and an analytical mind capable of applying mathematical reasoning to phenomena that had long been the domain of myth. Their work demonstrates that even with minimal technology, humans could make astonishingly precise measurements, and that the universe, vast as it is, could be approached incrementally, one calculation at a time. Hipparchus's catalogues, Aristarchus's geometric calculations, and Eratosthenes' measurement of Earth together form a lineage of empirical observation, leading to quantifiable knowledge, a lineage that defines the very nature of science. They reveal a process that would continue through history, identify patterns in nature, develop tools to measure those patterns, and apply mathematics to infer the scale and structure of the universe. The cosmos may have appeared infinite and unknowable to the naked eye, but through careful observation, human beings began to pierce the veil of the night sky, to assign numbers to stars, to estimate distances to the moon and sun, and to measure the very planet on which they stood. In retrospect, these early astronomers were not simply cataloguing stars or measuring Earth. They were laying the groundwork for the modern concept of the universe as a measurable entity. They demonstrated that with patience, ingenuity, and the right tools, humanity could move from myth to mathematics, from superstition to science, and from wonder to understanding. Their legacy is not just the numbers they recorded or the measurements they made, but the principle that the cosmos, no matter how vast, can be approached scientifically, systematically, and quantitatively. By the time their work was passed down through generations, the stage was set for a revolution in human understanding. The Renaissance would bring telescopes, the heliocentric model, and precise observations of planets. Centuries later, parallax measurements, Cepheid variables, and redshift would take these early efforts to unimaginable scales. But the seeds were planted by Hipparchus, Aristarchus, and Eratosthenes. The idea that the universe, however vast, could be measured, that numbers could describe distances and sizes, and that even a human standing on Earth could begin to grasp the cosmic expanse with nothing more than observation, reason, and a stick in the ground. Human understanding at the edge. The universe stretches far beyond anything we can directly observe, a vast expanse of galaxies, clusters, voids, and filaments, expanding and evolving over 13.8 billion years. Human understanding, however, has limits, not of curiosity, but of observation, measurement, and interaction. Telescopes reveal distant galaxies, gravitational waves trace ripples in space-time, and quantum experiments probe the foundations of matter and energy. Yet each instrument, no matter how sophisticated, confronts boundaries imposed by physics itself: the speed of light, cosmic expansion, quantum uncertainty, and the sheer scale of space. Science allows us to map, measure, and predict, but there are regions, phenomena, and scales where even the most advanced experiments reach their limits. The observable universe is defined by what light and information have had time to reach us. Galaxies beyond the horizon exist, yet their signals cannot traverse the expanding space to arrive at our instruments. The cosmic microwave background marks the earliest light we can see, a relic from 380,000 years after the Big Bang, beyond which we cannot observe directly. Even here, the universe was opaque, filled with a dense plasma that trapped photons, so the surface of last scattering forms a cosmic boundary for visual observation. We are always looking at a past we cannot fully reach, a universe whose present configuration remains partially hidden. Human understanding, then, is constrained by time as well as space. Yet our knowledge is not entirely passive. Gravitational waves offer a new lens, revealing cosmic events invisible to light-based observation. Black hole mergers, neutron-star collisions, and possibly primordial vibrations from the earliest moments of inflation. These waves traverse space unimpeded, carrying information about the dynamic universe, probing structures and processes that lie beyond our direct vision. Future missions like LISA will expand this capacity, mapping the curvature of spacetime and exploring phenomena at scales we have only theorized about. Through these observations, science pushes ever closer to the limits of what is knowable, extending understanding to regions and events that were once purely speculative. Quantum experiments further probe the edge of understanding. Entanglement, superposition, and quantum fluctuations challenge classical notions of locality, causality, and determinism. Laboratory studies of quantum mechanics provide insight into phenomena that govern the early universe and cosmic structure. Fluctuations in the vacuum during inflation may have seeded the formation of galaxies and cosmic filaments, demonstrating how microscopic uncertainties influence the macroscopic universe. At cosmic scales, quantum behavior interacts with gravity, producing singularities, black hole event horizons, and extreme energy regimes. These are regions where current theories break down, where general relativity and quantum mechanics clash, and where the universe reveals its deepest mysteries. Human understanding approaches these frontiers cautiously, using mathematics, observation, and experiment to navigate the unknown. Observational limits extend to the universe's expansion. Dark energy accelerates space, causing distant galaxies to recede faster than light can traverse the intervening space. These regions are forever beyond our reach, and no signal can bridge the gap. The universe has effectively isolated parts of itself from observation, creating permanent horizons. In these regions, we cannot measure, interact, or even infer details with certainty. The edges of knowledge are therefore dictated not by our instruments, but by the universe itself. Space-time and expansion define where science can operate, producing boundaries that are both absolute and elusive. Even in regions we can observe, unseen forces dominate. Dark matter shapes galactic rotation curves and the cosmic web, while dark energy drives accelerated expansion. These components constitute over 95% of the universe's content, yet remain largely invisible. Our perception, even aided by instruments, captures only a fraction of reality. Understanding requires indirect inference, modeling, and experimentation, linking observable effects to the unseen causes. Science interprets signals, reconstructs structures, and tests predictions, but we are always peering through a veil, glimpsing the universe in fragments, patterns, and shadows. Technology expands these observational limits. Telescopes like Hubble and James Webb peer deeper into space than ever before, revealing the first galaxies, primordial star clusters, and faint cosmic structures. Multi-messenger astronomy combines light, gravitational waves, neutrinos, and cosmic rays, integrating information across different carriers. Computational models simulate galaxy formation, dark matter distribution, and cosmic evolution, allowing humans to predict structures beyond observational reach. Quantum sensors, precision interferometry, and high-energy detectors extend experiments to extreme scales, probing the foundations of reality itself. Each advancement reveals the universe more fully, yet simultaneously exposes new horizons beyond comprehension. Experimental limits are similarly profound. Observing black hole interiors, quantum gravity effects, or cosmic phenomena at singularities is impossible with current physics. We can measure surrounding effects, accretion disks, relativistic jets, gravitational lensing, but the internal mechanisms remain inaccessible. Entropy, event horizons, and quantum uncertainty impose fundamental boundaries on knowledge. Experiments push to the edge of these limits, testing theories and exploring extreme conditions. Yet some aspects of the universe may always remain beyond direct experience. Science advances by probing these boundaries, turning limits into questions and questions into new frontiers of knowledge. Even our understanding of space and time itself is bounded. The universe may have dimensions beyond the 3 spatial and 1 temporal dimension we perceive. Extra dimensions, if they exist, are hidden from direct observation, potentially influencing forces, particle interactions, and cosmic structure. Cosmic expansion, quantum fluctuations, and gravitational effects may all carry signatures of higher dimensions. Yet detecting and interpreting them remains a formidable challenge. Human comprehension must therefore reconcile the observable, measurable universe with the possibility of hidden layers and unseen structures that define reality on scales beyond direct perception. In considering life, matter, and energy at cosmic extremes, we confront further boundaries. The observable universe presents familiar conditions: stars, planets, and galaxies composed of baryonic matter. Beyond this, extreme radiation, near absolute zero temperatures, high-energy cosmic events, and the influence of dark components define regions hostile to life as we know it. We can model behavior at these extremes, but direct interaction is impossible. Human understanding must therefore combine observation, theory, and experiment to explore realms that remain physically unreachable, using proxies and simulations to illuminate the cosmic frontier. The question of cosmic edges, horizons, and boundaries ties directly into the limits of understanding. Observationally, the speed of light and expansion define horizons beyond which direct perception is impossible. Experimentally, quantum mechanics, relativity, and extreme energy physics define boundaries where theories may fail or diverge. Computationally, simulations extend human reach, yet they depend on assumptions and models grounded in local observation. Together, these limits frame what it means to know the universe, highlighting that understanding is always partial, provisional, and evolving. Despite these boundaries, the human drive to explore persists. Future missions, advanced telescopes, quantum experiments, and gravitational wave observatories promise to extend the edge of knowledge, revealing previously hidden regions, forces, and phenomena. Observations of the first stars, mapping the cosmic web, detecting primordial gravitational waves, and probing quantum behavior at extreme scales, all push the frontier outward. Each discovery illuminates not just distant structures, but the rules and forces that govern the universe itself. Science advances by navigating limits, probing edges, and integrating data across scales, creating a richer and more detailed map of reality. The edge of human understanding is also defined by the interplay of observation and theory. Observations suggest structures, forces, and behavior. Theories interpret, predict, and extrapolate. This synergy allows knowledge to extend beyond direct perception, enabling reconstruction of cosmic history, the modeling of galaxy formation, and the testing of physical laws under extreme conditions. Even as we approach observational or experimental boundaries, theory illuminates possible realities, guiding future exploration and suggesting new frontiers. At the largest scales, the universe itself presents a dynamic and evolving boundary. Expansion, acceleration, dark energy, and dark matter shape the cosmic horizon, defining the limits of interaction. Quantum fluctuations seeded the earliest structures, yet remain hidden at small scales. Singularities, black holes, and extreme events define localized edges where current physics breaks down. Understanding these boundaries is central to probing the universe, testing the foundations of space-time, and exploring the interface between the observable and the hidden. Human understanding is ultimately a cumulative and iterative process. Observations refine models, experiments test predictions, and simulations extend reach. Each frontier conquered reveals new horizons, and every limit encountered challenges assumptions. Science advances not by reaching a final edge, but by exploring successive boundaries, translating observation into understanding, and illuminating realms that were previously inaccessible. The universe remains both a challenge and a guide, expanding faster than our perception, yet revealing patterns, principles, and structures that can be measured, tested, and understood. The edge is not merely a physical location. It is a frontier of knowledge, a space where curiosity meets limitation. Telescopes, gravitational wave observatories, quantum experiments and simulations illuminate what exists, how it behaves, and how it interacts. Observation captures snapshots, gravitational waves reveal dynamics, and quantum studies probe the underlying rules. Together, they provide a multidimensional approach to understanding the cosmos at its boundaries. Science teaches that the edge is both real and illusory. Observational limits, causal horizons, and quantum uncertainty define boundaries for measurement. Yet existence continues beyond these limits. Galaxies, dark matter, dark energy, and possibly other universes remain, beyond perception but real. Human understanding navigates this paradox, translating limited data into knowledge, creating models, and pushing the frontier ever outward. The edge of the universe is mirrored by the edge of comprehension, both vast, complex, and humbling. The universe as a frontier invites both awe and curiosity. Every new discovery, from distant galaxies to quantum fluctuations, challenges perception, expands understanding, and illuminates previously hidden structures. Future exploration, telescopes, gravitational waves, quantum experiments, and multi-messenger observations promises to reveal more of the cosmos, pushing human knowledge to regions currently beyond reach. The universe is a canvas of unimaginable scale, complexity, and mystery, where each edge encountered marks not an end, but an invitation to explore further. Are we really at the edge, or is it just the beginning? The question resonates not because we know the answer, but because the universe continues to expand, evolve, and reveal itself in ways that challenge perception. Human understanding is bounded, but each boundary is a frontier, a space for discovery, measurement, and insight. The cosmos is vast, layered, and dynamic, and every limit we encounter opens the possibility for new exploration. Reality extends far beyond perception, inviting us to push, probe, and imagine the vast reaches that lie beyond sight. The edge of human understanding and the edge of the universe are intertwined. Observation, experimentation, and theory illuminate regions within reach, while cosmic expansion, quantum uncertainty, and hidden energy structures define limits. Together, they create a vision of a universe that is vast, dynamic, and filled with phenomena beyond direct perception. Science does not merely map what exists, it defines what is knowable, reveals patterns, and challenges the assumptions of reality. Each horizon approached is both a boundary and an invitation, a frontier where curiosity meets the immense, unseen, and unknowable universe. The expansion of the universe. Look up at the night sky and it feels calm, still, frozen in place. Stars appear fixed. Galaxies look like distant islands, hanging quietly in the dark. But this calm picture is an illusion. The universe is not standing still. It is moving. It is stretching. Every second, space itself is expanding, carrying galaxies away from each other like dots painted on an inflating balloon. This discovery did not come from imagination or philosophy. It came from careful observation, precise measurement, and a quiet but revolutionary scientist named Edwin Hubble. Before the 20th century, many astronomers believed the universe was static and unchanging. The Milky Way was thought to be the entire universe, with fuzzy objects called nebulae scattered within it. No one imagined that space itself could expand. There was no concept of a universe growing larger with time. The idea that everything was once closer together, that galaxies were moving apart, simply did not exist in science. That changed when astronomers began to look deeper into space with more powerful telescopes. What they found would completely transform our understanding of the cosmos. Edwin Hubble was not searching for an expanding universe. He was trying to answer a simpler question. What are those faint, cloudy objects in the sky? Using the 100-inch Hooker telescope at Mount Wilson, the most powerful telescope of its time, Hubble focused on the Andromeda Nebula. This object appeared as a faint spiral smudge, visible even to the naked eye under dark skies. At the time, astronomers were divided. Some believed Andromeda was a cloud of gas inside the Milky Way. Others suspected it might be something far bigger, possibly a separate galaxy. The problem was distance. No one knew how far away Andromeda really was. Hubble solved this problem by studying Cepheid variable stars. These stars brighten and dim in a regular pattern. Crucially, the time it takes for a Cepheid to brighten and fade is directly linked to its true brightness. By comparing how bright the star truly is with how bright it appears from Earth, astronomers can calculate its distance. Hubble found Cepheid variables inside Andromeda. When he calculated their distance, the result was shocking. Andromeda was far beyond the edge of the Milky Way. It was not a cloud inside our galaxy. It was an entire galaxy of its own, containing billions of stars. This single measurement expanded the size of the known universe overnight. The Milky Way was no longer everything. It was just one galaxy among many. But this discovery was only the beginning. As Hubble continued his observations, he began to notice something strange. Light from distant galaxies was shifted toward the red end of the spectrum. This effect, called redshift, had been observed before, but its meaning was not fully understood. To understand redshift, think of sound. When an ambulance moves toward you, the siren sounds higher. When it moves away, the sound becomes lower. This is called the Doppler effect. Light behaves in a similar way. When an object moves toward us, its light shifts toward blue. When it moves away, its light shifts toward red. Hubble realized that the redshift of galaxies meant they were moving away from us. But the surprise came when he compared redshift with distance. The farther away a galaxy was, the faster it appeared to be moving away. This relationship became known as Hubble's law. The law states that the speed at which a galaxy moves away from us is directly related to its distance. In simple terms, the farther a galaxy is, the faster it is moving away. This does not mean Earth is the center of the universe. Every observer, no matter where they are located, would see the same thing. Galaxies are not flying through space away from a central point. Instead, space itself is expanding. A common way to picture this is with a balloon. Imagine dots drawn on the surface of a balloon. As the balloon inflates, every dot moves away from every other dot. No dot is at the center of the surface. The expansion happens everywhere at once. The universe behaves in the same way, except in 3 dimensions. Galaxies are mostly staying in place relative to their local surroundings, but the space between them is stretching. Redshift on a cosmic scale. Redshift is not just a motion effect. On the largest scales, it is a result of space-stretching light itself. As light travels across the universe, space expands along the way. The wavelength of the light becomes longer, shifting toward red. This is called cosmological redshift, and it is different from the Doppler effect caused by motion through space. Here, the light is stretched because the universe grows while the light is traveling. This means redshift is a direct measure of how much the universe has expanded since the light left its source. When we observe a distant galaxy with high redshift, we are seeing it as it was billions of years ago, when the universe was much smaller. Redshift allows astronomers to turn light into a time machine, revealing the history of cosmic expansion. Hubble's work depended on measuring distances accurately, something that had never been done on such large scales before. He used a method known as the cosmic distance ladder. This ladder starts with nearby objects whose distances can be measured directly. Those measurements are then used to calibrate brighter objects that can be seen farther away. Cepheid variables were a crucial rung on this ladder. By measuring Cepheids in nearby galaxies, Hubble established distances beyond the Milky Way. He then combined those distances with redshift measurements taken by other astronomers, especially Vesto Slipher, who had already measured galaxy spectra. The result was a clear pattern. Distance and redshift were linked. The universe was expanding. This discovery did not just add a new fact to astronomy. It changed the meaning of the universe itself. a universe that expands must have been smaller in the past. That idea would later lead directly to the Big Bang model. One of the most common misunderstandings is the idea that the universe exploded outward from a single point into empty space. That is not what expansion means. Expansion means that space itself is growing. There is no edge where galaxies are flying into nothing. There is no center from which everything moves away. Every region of space experiences expansion. This also means that very distant galaxies can move away from us faster than the speed of light. This does not violate physics, because they are not traveling through space faster than light. Space between us and them is expanding. The speed of light remains the limit for objects moving locally through space, but expansion works on a different rule. If the universe is expanding now, then in the past it must have been smaller. Run the expansion backward and galaxies get closer together. Go far enough back and the universe becomes extremely dense and hot. This idea connects directly to observations of the cosmic microwave background, the faint glow left over from the early universe. The expansion predicted by Hubble's law fits perfectly with this background radiation. Expansion also explains why distant galaxies look younger, smaller, and less developed. We are seeing them at an earlier stage of cosmic history, when the universe was still forming its structure. Hubble's discovery was made nearly a century ago, but it has been confirmed again and again with better instruments. Modern telescopes measure redshift with extreme precision. Space missions observe supernovae in distant galaxies to refine distance measurements. These observations show not only that the universe is expanding, but that the expansion is accelerating. Galaxies are moving apart faster now than they were in the past. This acceleration is driven by dark energy, an unknown form of energy that fills space itself. Expansion is not slowing down, it is speeding up. Expansion creates a natural limit to what we can see. Light from very distant regions may never reach us because space expands faster than the light can travel. This creates a cosmic horizon, not a physical wall, but a boundary of observation. Beyond this horizon, galaxies exist, but they are forever hidden from view. Expansion shapes not only the size of the universe, but the limits of knowledge itself. The universe does not end at this horizon. The expansion tells us that there is more space, more galaxies, more structure beyond what we can observe. Edwin Hubble's discovery transformed a quiet, static universe into a dynamic, evolving one. Galaxies are not fixed. Space is not still. The universe is alive with motion on the largest possible scale. Every second, the distance between galaxies grows. Every photon traveling through space is stretched. Every observation of deep space is also a look into the past. The expansion of the universe is not just a detail of cosmology. It is the framework that explains where the universe came from, how it changes, and why the edge of what we can see is not the edge of what exists. The night sky may look still, but the truth is far more dramatic. The universe is growing, carrying everything with it, pushing the limits of observation farther and farther away. Measuring distance in the universe is one of the most fundamental challenges in astronomy, because unlike objects on Earth, cosmic structures are far too distant to touch, measure directly, or even see clearly with the naked eye. Light is our only messenger, and by understanding how it travels and changes across vast distances, astronomers can begin to map the universe. One of the first methods for measuring distance relies on parallax, the apparent shift of a nearby star against the distant background as Earth moves in its orbit. This technique is straightforward in concept. The closer a star is, the more noticeable its apparent motion becomes. By measuring this tiny shift over months and applying geometry, astronomers can calculate how far away the star must be. Parallax works remarkably well for stars in our local neighborhood, providing an essential foundation for measuring distances within our own galaxy. Yet its reach is limited. Beyond a few thousand light-years, the shifts are so minuscule that even the most sensitive instruments struggle to detect them, leaving astronomers needing brighter and more distant markers to continue their cosmic measurements. For slightly farther reaches of the universe, the focus shifts to Cepheid variable stars, luminous stars that brighten and dim in a predictable rhythm. The beauty of these stars lies in the precise relationship between their pulsation period and their intrinsic brightness. By carefully timing how long a Cepheid takes to complete a cycle of brightening and dimming, scientists can determine exactly how bright the star truly is. Observing how dim it appears from Earth allows them to calculate its distance with astonishing accuracy. Cepheid variables shine brightly enough to be observed not just within our own galaxy, but also in neighboring galaxies, making them an indispensable tool for bridging the gap between local measurements and the far reaches of the cosmos. They are the first rung in a vast cosmic distance ladder, connecting nearby stars to entire galaxies and allowing astronomers to construct a coherent map of the universe on scales far larger than anything imaginable centuries ago. Yet even Cepheids have their limits. As astronomers pushed further into the depths of space, they required markers that could be observed across hundreds of millions or even billions of light years. Here, Type Ia supernovae became the ultimate standard candles. These extraordinary events occur when a white dwarf star reaches a critical mass and detonates in a predictable explosion, releasing a nearly uniform amount of light. Because the peak brightness of these supernovae is well understood, astronomers can calculate the distance to the galaxy in which they occur simply by comparing the apparent brightness observed from Earth. Type Ia supernovae are unimaginably bright, outshining entire galaxies for brief periods, and this incredible luminosity allows us to measure distances far beyond the reach of Cepheid variables. By observing these supernovae, scientists can trace the expansion of the universe itself, seeing how distant galaxies move away from us, and how the rate of that expansion changes over billions of years. These different methods are not isolated. They form a cosmic distance ladder, where each technique builds upon the one before. Parallax measurements establish a reliable scale for nearby stars, which calibrates the brightness of Cepheid variables in nearby galaxies. Those Cepheids, in turn, allow astronomers to confirm the brightness of Type Ia supernovae in distant galaxies. By linking these techniques, scientists can measure the universe from our solar neighborhood all the way to the most distant observable galaxies, creating a continuous chain of measurement that spans billions of light years. This ladder is more than a tool. It is the foundation for understanding cosmic expansion, mapping large-scale structures, and tracing the history of the universe from its earliest epochs to the present day. Distance measurement is intimately tied to our understanding of the universe's motion. By combining these methods with observations of redshift, astronomers can determine not only where galaxies are, but how fast they are receding from us. Cepheid variables and Type Ia supernova provide the scales, and redshift provides the speed. Together, they reveal a universe in motion, expanding in every direction, and set the stage for discovering that space itself is stretching. Without precise distance measurements, the redshift of a galaxy could be interpreted in many ways. But by knowing the distance accurately, astronomers can directly measure the relationship between distance and recessional speed, formulating what became known as Hubble's law. The distance ladder makes this possible, transforming abstract light measurements into a quantitative map of cosmic expansion. The ability to measure cosmic distances has changed our perception of the universe. Where once the Milky Way was thought to contain all that exists, we now understand it as just one galaxy among billions. Accurate distance measurements allow scientists to place galaxies within clusters and superclusters, revealing the large-scale structure of the universe and the cosmic web of filaments and voids. They also allow the precise calculation of the Hubble constant, the rate at which space expands, which in turn informs models of the universe's age, size, and ultimate fate. Each rung of the distance ladder, from parallax to Cepheids to supernovae, extends our vision, providing the framework that turns mere points of light into a coherent, measurable, and comprehensible cosmos. The observable universe. The universe stretches far beyond the limits of human imagination, filled with countless galaxies, clusters, and structures woven across an unfathomable expanse of space and time. Yet, despite its vastness, the portion of the cosmos that we can interact with, measure, and observe is limited, bounded by fundamental rules of physics and the finite speed at which information travels. This portion is what astronomers call the observable universe, a sphere centered on Earth, defined not by a physical barrier, but by the very nature of light and time. The observable universe exists because the universe has a finite age, approximately 13.8 billion years, and nothing can travel faster than the speed of light. Light emitted from distant galaxies over cosmic history has taken time to reach us, and because the universe is not infinitely old, we can only see signals that have had enough time to traverse the expanding cosmic fabric. Everything beyond this limit remains hidden from view, not because it does not exist, but because its light has not yet arrived and may never arrive if cosmic expansion outpaces the travel of photons. The cosmic horizon is the boundary of this observable domain, representing the maximum distance from which light or other signals can reach us today. This horizon is not a static wall or a literal edge of space. It is a moving frontier that expands with time as light from more distant objects gradually reaches us. Its position depends on the interplay between the age of the universe, the speed of light, and the stretching of space itself due to cosmic expansion. Because space is expanding, objects that were once close to us may now lie far beyond the reach of their light, ever intersecting our line of sight. Conversely, light emitted from extremely distant regions long ago may now be arriving at Earth, allowing us to glimpse galaxies as they appeared billions of years ago, in forms radically different from how they exist today. This interplay between distance, time, and expansion creates a dynamic, shifting boundary that defines the limits of observation. You see, to understand the observable universe, you need to know how light serves as both a messenger and a clock. Every photon arriving from a distant star, galaxy, or supernova carries with it information about the state of that object at the time the light began its journey. When we look at the Andromeda galaxy, we see light that has traveled for over 2 million years, capturing Andromeda's appearance in the distant past. When we observe galaxies billions of light years away, we are witnessing their infancy, the processes that formed stars, clusters, and early cosmic structure. The finite speed of light turns the universe into a layered time capsule, allowing observation of epochs that no other method could access. This temporal layering is intrinsic to the concept of the observable universe because it limits not only spatial reach but also temporal perception. We never see objects as they are in the present, but as they were when the light began its journey. The size of the observable universe, measured in terms of light travel distance, is not identical to the distance between us and the farthest objects in today's space. Space itself expands while light is traveling, stretching the distance between galaxies as they recede from one another. This means that although the universe is 13.8 billion years old, the current proper distance to the edge of the observable universe is far greater, approximately 46 billion light-years in all directions. This enormous scale reflects not only the age of the universe, but also the continuous stretching of space itself, highlighting the distinction between what we see and where the matter we see actually resides. Light from the earliest galaxies has been traveling for most of cosmic history. Yet those galaxies have been carried even farther away by the expansion of space, creating a vast volume beyond the simple calculation of age multiplied by the speed of light. The observable universe is more than just a concept of distance. It defines the limits of causality and information exchange. Beyond the cosmic horizon, signals from matter cannot influence us, and we cannot influence them. Events occurring in these regions remain forever disconnected from Earth, and no observation, no signal, and no physical interaction can bridge the gap. This does not imply a termination of reality, merely a boundary to what is accessible. Every measurement, every astronomical observation, and every cosmic survey operates within the constraints imposed by this horizon, shaping the scope of knowledge and the framework within which cosmology operates. Observing the universe also entails recognizing the cosmic microwave background, CMB, as a fundamental marker of observational limits. The CMB represents the oldest light that can reach us, originating roughly 380,000 years after the Big Bang, when the universe cooled enough for photons to travel freely through space. This relic radiation defines a surface beyond which direct observation is impossible. The universe was opaque before this era, filled with a dense plasma that trapped light. The CMB forms the ultimate boundary for electromagnetic observation, a glowing backdrop marking the edge of the observable universe in terms of visible signals. Studying its fluctuations and temperature variations reveals information about the distribution of matter, the density of the universe, and the seeds of structure formation, while simultaneously emphasizing that any region beyond this surface remains hidden from direct view. The concept of the observable universe also interacts with cosmic expansion and the dynamics of space-time. As the universe grows, galaxies recede from one another, and the boundary of what can be observed slowly shifts outward. Some regions, however, move away faster than light due to expansion, meaning their light will never reach us. This creates a complex structure in which some parts of the universe are observable. Some will become observable in the far future, and others are permanently beyond reach. The observable universe is therefore not a fixed sphere, but a time-dependent horizon, expanding as the universe ages and as photons from ever-distant objects finally reach Earth. Even within this observable volume, apparent distances and ages are nuanced. Galaxies observed at extreme distances are seen as they were billions of years ago, and their light has been stretched by the expansion of space, producing a redshift that encodes both velocity and cosmic history. Interpreting these signals requires careful application of general relativity and cosmological models, as simple arithmetic cannot account for the combined effects of light travel, time, expansion, and curvature of space. Each observation is a combination of position, motion, and epoch, layered into a cosmic story that astronomers decode to understand structure formation, galaxy evolution, and the distribution of matter across the universe. The observable universe also implies a perspective-dependent horizon. Every point in space has its own observable universe, a sphere centered on that location. From another galaxy, the observable universe would look different, with some regions we can see today hidden behind that observer's horizon and other regions revealed. This illustrates that the observable universe is a limit of perception rather than a physical boundary, defined entirely by the interplay of light travel, expansion, and time elapsed since the Big Bang. In principle, countless other observers exist, each with a cosmic horizon of their own, and together they form a universe whose total size may be far greater than any one observer can witness. The interplay of light speed, cosmic age, and expansion also raises deep questions about the nature of limits. While the observable universe is finite in radius, it may only represent a tiny fraction of the total cosmos. Beyond the horizon, matter, galaxies, and structures continue to exist, potentially infinitely, but remain forever inaccessible. These regions may follow the same physical laws we observe locally, or they may host structures shaped by subtle variations in density, dark matter, or dark energy. The observable universe is a window into a much larger, largely unseen reality, providing constraints on theory while leaving open the possibility that the true universe is far more extensive, complex, and dynamic than what can ever be measured. The concept of the observable universe therefore frames both what we can know and how we understand cosmic history. It sets the stage for all measurements of galaxy distribution, cosmic microwave background analysis, and the study of large-scale structure. It also defines the limits within which astronomers can test theories about the origin, evolution, and ultimate fate of the universe. Beyond it, speculation must give way to inference, modeling, and theory, as no light, no signal, and no observation can provide direct knowledge. The observable universe is a dynamic, evolving boundary, stretching outward with every passing second as light from more distant regions finally arrives, offering glimpses of epochs and structures previously hidden. The observable universe is the realm in which human measurement and observation are possible, a sphere defined by the fundamental laws of physics rather than walls or edges. Its size, marked at roughly 46 billion light-years in radius, represents both the limits of human observation and the immense scale over which cosmic expansion has unfolded. Every galaxy we detect, every photon we measure, and every structure we map exists within this horizon. Beyond it lies the unknown, a vast expanse where galaxies continue, forces operate, and matter evolves, entirely hidden from view. The observable universe is both a measure of cosmic reach and a testament to the power of light and time to shape our perception, revealing a universe that is incomprehensibly vast, yet partially knowable. A frontier defined by physics, patience, and the unending journey of observation. Infinite universe theories. When we look at the night sky, it feels endless, right? Stars everywhere, galaxies sprinkled like sugar, nothing stopping the view. But what about the universe itself? Is it truly infinite, stretching forever in every direction, or does it have a shape, a curve, a boundary we can't see? For decades, scientists have been asking this question, trying to figure out the shape of everything. The answer isn't easy, because we can't just step outside the universe and measure it. Instead, we rely on clever physics, patterns in light, and the faint whispers of the cosmos that have traveled billions of years to reach us. One way scientists think about the universe is like this. Imagine space itself as a sheet, like a huge rubber sheet or a trampoline. Now, the sheet can be flat, it can curve like a sphere, or it can curve the other way like a saddle. These shapes aren't just ideas. They determine how the universe expands, how gravity works on cosmic scales, and even what might happen to the universe billions of years from now. This is where the Friedmann-Lemaitre-Robertson-Walker metric, or FLRW for short, comes in. Think of it as a mathematical map of the universe's shape and how it stretches over time. It tells us, in the simplest terms, whether space is flat, curved, or bent in some more extreme way. A flat universe is the simplest to imagine. Picture a sheet of paper stretching endlessly in all directions. Parallel lines never meet. Angles of triangles add up to 180 degrees. Light travels in straight paths, and the expansion of space moves everything away from everything else in a simple, predictable way. Flatness is kind of magical because it means the universe doesn't curve back on itself, and it doesn't loop endlessly like a sphere. In this model, if you traveled forever in one direction, you would keep going without ever returning to where you started. Then there's a curved universe, and here things get a little stranger. A positively curved universe is like the surface of a sphere. If you draw a triangle on a sphere, its angles add up to more than 180 degrees. Lines that look straight eventually meet. In a positively curved universe, if you traveled far enough in one direction, you could end up back where you started, just like circumnavigating the Earth. Space wraps around itself, and the universe could be finite but still have no edge. On the other side, a negatively curved universe looks like a saddle. Triangles have angles that add up to less than 180 degrees, and space stretches out infinitely, bending in a way that creates a weird, open geometry. So how do we know which of these applies to our universe? We can't just measure curvature with a ruler, obviously. Instead, scientists turn to the cosmic microwave background, or CMB, which is like the oldest photograph of the universe we can get. The CMB is light that was released roughly 380,000 years after the Big Bang, the first time photons could travel freely. It's faint, it's ancient, and it carries information about the density, temperature, and curvature of the early universe. Tiny patterns in the CMB, spots that are slightly hotter or cooler, can tell us whether space is flat, closed, or open. If the universe is flat, the angles we see in the CMB's patterns match what we expect from Euclidean geometry, the kind you learned in school. If it's curved, those angles shift slightly. Observations from satellites like COBE, WMAP, and Planck have measured these angles with incredible precision, and the results are stunning. The universe appears to be flat to within a fraction of a percent. That doesn't just mean it's geometrically simple. It tells us something profound about the early universe, its energy content, and even the mysterious force we call dark energy, which drives expansion. But flatness opens more questions than it answers. A perfectly flat universe, combined with observations of expansion and matter density, suggests that the universe could be infinite. If it stretches out forever, there is no end, no edge, and every direction goes on eternally. That blows the mind, because we are used to thinking in terms of walls, borders, and edges. Yet cosmology suggests that at least on the largest scales, there might not be any edge at all, just endless space, galaxies, and stars continuing beyond what we can ever see. Open and closed universes add twists to this story. A closed universe could eventually slow its expansion, stop, and even collapse back on itself in a big crunch, while an open universe would continue stretching forever, expanding into nothingness, with galaxies moving further apart at speeds we can barely imagine. Flatness sits right in the middle. It expands forever, but just at the critical rate needed to balance gravity and energy density. Observations of the CMB suggest that our universe is remarkably close to this balance, but the question of infinity remains. Flatness allows for it, but it doesn't guarantee it. The universe could be flat and finite in ways we can't perceive, or it could stretch endlessly. The geometry of the universe also affects how we see distant galaxies, clusters, and superclusters. In a curved universe, light doesn't travel in straight lines, so distant objects appear warped, their apparent sizes shifted. Flatness ensures that the universe looks roughly the same in every direction at the largest scales, which matches the cosmological principle, the idea that the universe is homogeneous and isotropic, the same everywhere on large scales. Observations of the CMB confirm this principle to an astonishing degree, showing tiny temperature fluctuations but overall uniformity, supporting the notion that the universe is flat and possibly infinite. Infinity is hard to wrap your head around. If the universe truly stretches forever, then for every galaxy we see, there are countless more beyond our reach. Beyond the cosmic horizon, galaxies exist that we can never observe because their light will never reach us. Yet, if space is infinite, there are even entire regions with matter, energy, and even possible variations in physical properties that remain completely out of sight. Our observable universe is only a tiny bubble in this unimaginable vastness, a limit imposed by the speed of light and the finite age of the cosmos, not by the universe itself. Understanding the universe's shape also connects to cosmic inflation, a period of extremely rapid expansion in the first fraction of a second after the Big Bang. Inflation would have stretched space so much that any initial curvature would have been smoothed out, leaving the universe flat on the largest scales we can see. This fits perfectly with CMB measurements and the apparent flatness of our observable universe. Inflation also hints at something stranger. If inflation continues elsewhere, there could be countless other bubble universes, each with its own shape, expansion, and possibly even different laws of physics. Our universe might be just one part of an infinite, mind-boggling multiverse. The combination of geometry, curvature, and observations also shapes how we understand cosmic destiny. A closed universe might one day collapse. An open universe might expand forever, thinning matter until galaxies drift beyond each other's influence. A flat universe expands indefinitely, but the balance between gravity and dark energy determines whether structures like galaxies and clusters remain intact or eventually drift into isolation. Each shape implies a story, a fate, and a perspective on how the universe evolves over billions of years. Even with all this knowledge, The infinite universe remains both tantalizing and mysterious. Flatness suggests endless space, but what lies beyond the observable horizon is unknown. Curvature allows loops and folds, yet we see little evidence of such structure. The cosmic microwave background gives us hints, tiny clues frozen in ancient light, yet it can only show what is within reach. Beyond that, physics lets us speculate but not directly observe. Infinity is a concept, a horizon we can approach in thought if not in reality, a scale so vast that even billions of galaxies are just a fraction of the whole. The debate between flat, open and closed universes is not just academic. It shapes our understanding of cosmic evolution, the growth of structure, and the ultimate limits of observation. Flatness, as we see in CMB measurements, points toward an infinite or near-infinite cosmos, one that continues far beyond our telescopes and instruments, one that stretches our imagination as much as it stretches space itself. Every new measurement, every tiny fluctuation detected in the CMB, every supernova observed billions of light years away, adds a brushstroke to this portrait, revealing a universe that is simple in shape yet vast beyond comprehension. Our universe, in all its infinite potential, challenges perception. Flatness hints at infinity, yet the cosmos remains a horizon away, unreachable and mysterious. It expands, it stretches, and it curves in ways we measure with incredible precision. Yet even with the best instruments, we only see a fraction. Beyond lies more space than the human mind can picture, perhaps truly endless, a canvas on which galaxies, dark energy, and the laws of physics continue to operate. The observable universe gives us a window, but flatness suggests that window opens onto something that never ends, a stage set for unimaginable cosmic drama. Cosmic microwave background, the universe's echo. Imagine the universe as a vast, dark ocean, stretching endlessly in all directions, mostly invisible to the human eye. Now imagine a faint ripple frozen across that ocean, a whisper that has traveled for more than 13 billion years, carrying the story of the universe's earliest moments. This whisper is the cosmic microwave background, or CMB, and it's the oldest light we can ever observe. It's the afterglow of the Big Bang, a faint glow permeating every corner of space. And it tells us a story that no telescope could have imagined before the mid-20th century. The story of the CMB begins in the 1960s with two physicists working in a New Jersey laboratory, Arno Penzias and Robert Wilson. They were not searching for ancient cosmic light. Their job was far more down to earth, studying radio signals and trying to understand why their equipment picked up a mysterious, persistent noise. This noise was everywhere, coming from all directions, day and night, and it could not be traced to Earth, the atmosphere, or any instrument fault. At first, they even wondered if it was a problem with pigeons nesting in the antenna. But after careful work, they realized this noise was real. It was a faint radiation coming from the universe itself. At the same time, theoretical physicists were predicting exactly such a phenomenon. According to Big Bang theory, the universe began in an extremely hot, dense state filled with light and energy. As it expanded, it cooled, and after about 380,000 years, it became transparent. Before that moment, light could not travel freely because the universe was like a dense fog of charged particles. But as atoms formed and the fog cleared, photons escaped for the first time. These photons have been traveling ever since, stretching and cooling with the expansion of space, and they now reach us as microwaves, radiation that is faint but measurable across the entire sky. Penzias and Wilson had stumbled upon this signal, confirming a prediction decades old and giving humanity its first direct glimpse of the universe's infancy. The CMB is more than just a faint glow. It is a snapshot of the universe when it was only 380,000 years old. In cosmic terms, that is almost nothing. Our universe is 13.8 billion years old. Yet this snapshot is profound because it captures the universe in a state that is almost primordial, long before galaxies formed, long before stars and planets, when the cosmos was a hot, nearly uniform soup of particles and radiation. Studying this snapshot allows scientists to see the seeds of everything that exists today: the galaxies, clusters, and cosmic structures that populate space. But the CMB is not perfectly uniform. It has tiny variations in temperature, anisotropies, that are just a few parts in 100,000. These small fluctuations are incredibly important. They reflect slight differences in density in the early universe. Regions that were slightly denser than average would eventually collapse under gravity to form galaxies and clusters. Regions that were slightly less dense became the vast cosmic voids between these structures. In other words, the patterns in the CMB are the blueprint for the entire cosmic web, frozen in place billions of years ago. To understand these patterns, scientists have mapped the CMB across the entire sky using sensitive instruments. The first full sky maps were produced by the COBE satellite in the 1990s, showing temperature variations with unprecedented precision. Later missions like WMAP, Wilkinson Microwave Anisotropy Probe, and the Planck satellite improved the resolution even further, revealing millions of tiny spots and ripples in the CMB. These maps allow researchers to calculate the angular power spectrum, which shows how the intensity of fluctuations varies with scale. Large-scale fluctuations tell us about the overall geometry of the universe, while smaller-scale fluctuations reveal how matter began to clump and form structure. One fascinating phenomenon observed in the CMB is the Sachs-Wolf effect, named after the physicists who described it. This effect occurs because the gravitational fields of massive structures affect the energy of photons traveling through them. As CMB photons pass through regions of slightly higher or lower gravitational potential, their energy shifts slightly, creating subtle patterns in temperature. Detecting and analyzing these tiny shifts allows scientists to measure the influence of matter on cosmic scales and to understand how the universe evolved after the CMB was emitted. The CMB also helps us determine the curvature of space. By analyzing the angular size of fluctuations in the CMB, scientists can infer whether the universe is flat, closed, or open. In a flat universe, light travels in straight lines, and the observed patterns match what we expect from Euclidean geometry. In a curved universe, light bends, and the patterns appear distorted. The precision of WMAP and Planck measurements has shown that the universe is extremely close to flat, with any curvature so tiny that it is almost undetectable. This insight is one of the strongest pieces of evidence that the cosmos stretches far beyond what we can see, possibly infinitely, and that the universe has a uniform, predictable structure on the largest scales. The beauty of the CMB is that it is cosmic archaeology at its finest. Each photon reaching Earth carries information from a time when the universe was still in its infancy. Scientists decode this information, extracting details about the universe's composition, temperature, density, and even the mysterious dark matter and dark energy that shape cosmic expansion. The CMB is not just light, it is a story, frozen in time, telling us how the universe started, how it expanded, and how it grew into the vast structures we see today. Even more amazing is that the CMB is visible everywhere, no matter where you are in the universe. Unlike galaxies or stars, which may be too distant or hidden by dust, the CMB bathes all of space uniformly. Wherever an observer exists, the CMB would appear roughly the same, a nearly uniform background with the same tiny ripples. This universality confirms that the laws of physics operate consistently across the cosmos, that the early universe behaved in ways we can model, and that the CMB is truly a window into the universe's origin. Mapping the CMB is not just about making pretty pictures. The detailed analysis of its anisotropies provides the most precise measurements of fundamental cosmic parameters, including the universe's age, its total matter content, and the ratio of ordinary matter to dark matter and dark energy. Tiny temperature differences in the CMB allow cosmologists to reconstruct the expansion history of the universe, revealing not only where it came from, but also how fast it is stretching today, and how it will continue to expand in the future. The cosmic microwave background is the ultimate time machine. letting us look directly at the universe when it was a newborn, billions of years before life, stars, or galaxies existed. It is a faint, uniform glow that fills space, studded with tiny fluctuations that carry the blueprint of all cosmic structure. Satellites like WMAP and Planck have mapped these fluctuations in incredible detail, letting scientists measure the universe's curvature, density, and expansion history. Phenomena like the Sachs-Wolf effect reveal the subtle interactions between gravity and light, encoding information about how matter influenced the early universe. Cosmic microwave background, the universe's echo. One of the most exciting aspects of the CMB is how it constrains the curvature of space. By measuring the angular size of the temperature fluctuations across the sky, cosmologists can determine whether the universe is flat, closed, or open. The physics behind this is subtle but powerful. In a flat universe, the size of these fluctuations appears exactly as predicted by simple geometry, like drawing triangles on a piece of paper. In a closed universe, the fluctuations appear slightly larger, as if space itself were wrapping around, bending light paths inward. In an open universe, the fluctuations appear smaller, as if space stretches light apart. By comparing detailed observations from satellites like Planck with theoretical models, scientists can measure curvature with astonishing precision. The results are mind-blowing. The universe is flat, at least to within a tiny fraction of a percent, confirming that space stretches smoothly and uniformly on the largest scales we can see. Beyond curvature, the temperature anisotropies in the CMB reveal the primordial seeds of structure. Some regions are slightly hotter, some slightly cooler, and these differences correspond to variations in matter density shortly after recombination. Denser regions would eventually attract more matter through gravity, growing into stars, galaxies, and clusters. Less dense regions became cosmic voids. These tiny fluctuations are the fingerprints of cosmic evolution, showing how the chaotic early universe organized itself into the magnificent web of galaxies we see today. The angular power spectrum of the CMB is another crucial tool. This spectrum is essentially a map of how the temperature differences are distributed across different scales in the sky. Large-scale fluctuations tell us about the overall geometry and average density of the universe. Medium-scale variations reveal how acoustic waves, ripples of matter and energy, move through the early plasma before photons decoupled. Small-scale fluctuations show the fine-grained structure that eventually formed galaxies. By analyzing this spectrum, scientists can calculate the amount of ordinary matter, and dark energy in the universe, providing a cosmic inventory that has never been possible before. The Sachs-Wolf effect also plays a starring role in decoding the CMB. This subtle phenomenon occurs because photons climbing out of gravitational wells lose a tiny bit of energy, while those falling into wells gain a bit. These tiny energy shifts are imprinted on the CMB as slight temperature variations. By studying these patterns, scientists can measure how matter and gravity interacted in the early universe and understand the distribution of large-scale structures. The Sachs-Wolf effect links the invisible pull of gravity to the light that has traveled billions of years, giving us a way to measure what otherwise could never be seen directly. Satellites like WMAP and Planck transformed our understanding of the CMB. WMAP produced the first detailed full-sky map, revealing millions of tiny fluctuations, and Planck improved the resolution to unprecedented clarity. These missions didn't just measure temperature, they also studied polarization, the orientation of light waves, which carries information about the earliest interactions of photons and electrons. Polarization data provides insight into the process of reionization, when the first stars lit up the universe, and even hints at gravitational waves from the earliest moments after the Big Bang. By combining temperature and polarization maps, cosmologists can test theories of inflation, the rapid expansion of space in the first fraction of a second, and verify whether the universe really did start in a near-uniform, super-hot state. The CMB also gives clues about the size of the universe. By analyzing the distribution and scale of fluctuations, scientists can estimate the total energy content, the density of matter, and how space itself has expanded over time. This, in turn, constrains models of the universe's fate, whether it will continue expanding forever, slow down, or collapse. In addition, the isotropy of the CMB, the fact that it looks almost the same in every direction, suggests that the universe is incredibly uniform on the largest scales. Yet the tiny ripples in the CMB remind us that this uniformity is not perfect, and those imperfections became the building blocks for everything from stars to galaxies, to clusters spanning millions of light years. Another fascinating aspect is that the CMB allows us to peer beyond the observable universe indirectly. While we cannot see past the cosmic horizon, the statistical patterns of fluctuations in the CMB hint at what might exist beyond. For example, the uniformity of temperature across opposite sides of the sky suggests that, before recombination, these regions were in contact through processes like inflation, even if they are now separated by distances greater than light could ever travel. In this sense, the CMB is a window into regions of the universe we can never directly observe, a messenger from the unseen beyond the horizon. CMB measurements also support the notion of inflationary bubbles and the multiverse, at least theoretically. Tiny anomalies or asymmetries in the CMB could hint at regions of space where inflation behaved slightly differently, potentially creating other pocket universes. While we cannot observe these directly, the CMB gives indirect evidence that our universe might be part of a much larger, more complex cosmos, with boundaries that are fundamentally beyond detection. Studying the CMB is like listening to a whisper from the dawn of time. Every photon carries information about density, temperature, curvature, and the interplay of light and gravity. It tells us about dark matter, invisible but massive, shaping the patterns we see. It hints at dark energy, the mysterious force stretching space and accelerating expansion. It allows scientists to measure cosmic distances, map structures, and calculate the exact age of the universe with incredible precision. The cosmic microwave background is more than light. It is a cosmic blueprint. It encodes the story of the universe before galaxies, before stars, before life, when everything was a nearly uniform plasma, vibrating with tiny ripples. Through meticulous measurements of anisotropies, polarization, and the angular power spectrum, we can reconstruct this ancient state, understand the universe's geometry, and even test ideas about physics that occurred in the first trillionths of a second after the Big Bang. The CMB also serves as a reminder of how human curiosity transforms the universe into something measurable and understandable. A faint static in a radio antenna became a portal to the beginning of time, and satellites like WMAP and Planck turned that portal into a detailed map, revealing the structure, composition, and evolution of everything around us. Each pixel in the CMB sky carries information about density, temperature, and the gravitational influence of matter, telling us not only where we came from, but how the universe organizes itself at the largest scales. Even after decades of study, the CMB continues to inspire new questions. Tiny anomalies in the data, unexplained alignments or asymmetries challenge scientists to refine theories, consider new physics, and imagine possibilities beyond what can be directly observed. It is a cosmic canvas, alive with information, whispering secrets from the dawn of the universe, hinting at regions beyond our reach, and encoding the subtle interplay between matter, energy, and the very fabric of space-time. Large-scale structure of the universe. When you look at the night sky, it seems like stars are scattered randomly across the darkness. But if you zoom out, way, way out, beyond the Milky Way, beyond neighboring galaxies, a hidden pattern starts to emerge. The universe is not just a random sprinkling of galaxies, it's a cosmic web, a vast, intricate network of matter stretching across unimaginable distances. On the largest scales, galaxies aren't isolated. They gather in clusters, Clusters combine into superclusters, and filaments of matter stretch between them, weaving the scaffolding of the cosmos. And in between those filaments lie enormous empty regions known as cosmic voids, where galaxies are few and far between. This structure, which astronomers call the large-scale structure, is the skeleton of the universe, and understanding it is like discovering the blueprint behind everything we see. Clusters of galaxies are like cities of the universe, dense hubs where thousands of galaxies gather together, bound by gravity and dark matter. Some clusters form part of even larger conglomerations called superclusters, sprawling across hundreds of millions of light-years. Filaments connect these clusters, forming highways of matter along which galaxies and gas flow. And then, between these highways, lie the cosmic voids, immense expanses of almost nothingness, stretching tens or even hundreds of millions of light-years. These voids are not completely empty, but they are regions where matter is thinly spread, almost as if the universe itself took a deep breath and left pockets of space untouched. The contrast between dense clusters, tangled filaments, and vast voids gives the cosmos a lace-like structure, delicate yet massive, chaotic yet organized, revealing the invisible threads of gravity and dark matter weaving everything together. Mapping this cosmic web is no small feat. Astronomers can't just take a picture and see all the filaments and voids. They are too vast, too faint, and too distant. Instead, scientists rely on galaxy surveys, massive projects that measure the positions and distances of millions of galaxies. One of the most famous of these is the Sloan Digital Sky Survey, SDSS. SDSS has mapped millions of galaxies across a huge portion of the sky, providing an unprecedented 3D view of the cosmos. Another groundbreaking effort was the 2DF Galaxy Redshift Survey, which measured redshifts for hundreds of thousands of galaxies, allowing astronomers to determine their distance and motion. By combining all this data, researchers can create a three-dimensional map of matter, revealing clusters, superclusters, filaments, and voids in stunning detail. Redshift surveys are the key tool in this exploration. As galaxies move away from us due to the universe's expansion, their light stretches, shifting toward longer wavelengths, a phenomenon called redshift. By measuring how much the light is stretched, astronomers can calculate how far away each galaxy is and how fast it's moving. This is not just a matter of mapping positions in the sky. It's about building a cosmic map in 3 dimensions, showing not only where galaxies are, but also how they are moving relative to one another. With these 3D maps, the universe transforms from a flat sky of dots into a dynamic, tangled web, where filaments twist, clusters clump, and voids yawn across unimaginable distances. What makes this structure even more fascinating is how it connects to cosmic history and geometry. The patterns we see today, the size of clusters, the spacing of filaments, the emptiness of voids, are fossilized records of the universe's growth over billions of years. Tiny fluctuations in the early universe, seen in the cosmic microwave background, were stretched and amplified by gravity, eventually forming the cosmic web. By studying the large-scale distribution of galaxies, astronomers can infer not just the evolution of structure, but also the underlying geometry of the universe. Is space flat, open, or closed? How much matter is there, and how much is invisible dark matter holding everything together? Every filament and void helps answer these questions. These maps also hint at the possibility of infinity. The cosmic web we see is enormous, spanning billions of light-years. Yet even this vast structure is only a fraction of the universe. Beyond the reach of our telescopes and surveys, there could be more clusters, more filaments, and more voids, stretching endlessly. The way matter is distributed, the patterns of clustering and spacing, suggest that on the largest scales, the universe is homogeneous, uniform in its structure, supporting the idea that it might extend infinitely in every direction. By measuring the distribution of galaxies, astronomers are not just studying matter, they are peering at the universe itself, trying to understand the shape and extent of everything. The large-scale structure also shows the hidden influence of dark matter. Visible galaxies are only the tip of the iceberg. The filaments and clusters are mostly held together by dark matter, an invisible substance that outweighs ordinary matter 5 to 1. Without dark matter, the cosmic web would not form. Gravity from ordinary matter alone isn't enough to create the vast interconnected network we observe. By mapping galaxies, astronomers indirectly map dark matter, tracing the unseen skeleton that holds the universe together. Observing the cosmic web is like exploring a massive three-dimensional city at a scale impossible to imagine. Clusters are the bustling downtowns, filaments the highways connecting them, and voids the empty suburbs of space. Each structure tells a story about gravity, expansion, and the distribution of matter. Each galaxy is a character in the drama of cosmic evolution, moving along the filaments, falling into clusters, or drifting across the emptiness of voids. And while the CMB gave us the universe's blueprint, the cosmic web shows the results of billions of years of cosmic growth, a living map of how the early fluctuations became the grand structure of today. Even as surveys grow, the universe continues to surprise. Tiny anomalies in filament thickness, unusual voids, or unexpected cluster shapes challenge theories and push scientists to refine models of gravity, dark matter, and cosmic expansion. Mapping the large-scale structure is not just a cataloging exercise, it is a window into the fundamental laws of the universe, a way to test our understanding of how space itself behaves and how matter organizes itself over unimaginable scales. Large-scale structure of the universe. The vast network of clusters, filaments, and voids is more than a pretty pattern. It's a map of cosmic history and the forces shaping everything, a tool for measuring distances, testing physics, and even glimpsing the possible infinity of space. One of the most powerful insights comes from redshift surveys, which measure not just where galaxies are, but how fast they are moving away from us. This motion isn't random, it's driven by the expansion of the universe. When we compare the redshift of a galaxy to its position in a 3D map, we can trace how matter has flowed over billions of years, showing how clusters formed, how filaments stretched, and how voids emptied. The distribution of galaxies in these surveys forms patterns that are not arbitrary. They reflect the underlying geometry of space itself. Subtle differences in clustering over billions of light years can reveal whether space is flat, curved, or even infinite, letting astronomers test the predictions of cosmology on the grandest scales. Surveys like SDSS and 2DF do more than just collect data. They allow scientists to perform statistical measurements of galaxy clustering. By calculating how likely galaxies are to be near one another at different distances, cosmologists can infer the density fluctuations in the early universe. These fluctuations, first imprinted in the cosmic microwave background, have grown over billions of years to form the cosmic web. By comparing observed clustering to predictions from theory, we can measure the amount of dark matter present, which dominates the mass of the universe and pulls galaxies into the filamentary structures we see today. Without dark matter, these filaments would be far less pronounced, and clusters would struggle to form. Mapping large-scale structure also helps us understand baryon acoustic oscillations, BAO, a subtle ripple in the density of matter left over from the early universe. BAO acts like a cosmic ruler, giving astronomers a standard scale to measure distances across space. By studying how galaxy clustering changes over different scales and distances, we can test models of cosmic expansion, track the influence of dark energy, and even refine our estimates of the universe's age. The cosmic web, in this sense, is more than structure. It's a laboratory for understanding the fundamental laws that govern the cosmos. Void regions, though seemingly empty, are equally important. These enormous expanses of low matter density act as natural laboratories for testing gravity and expansion. Because voids contain far less dark matter and fewer galaxies, the way they grow and evolve over time is sensitive to the physics of dark energy. Observing the shapes, sizes, and distribution of voids allows cosmologists to constrain models of the universe's expansion and to ask questions about whether the universe is truly infinite or just extremely large. The large-scale structure also offers hints about the possible infinity of the universe. By examining the uniformity and statistical properties of galaxy clustering across immense distances, scientists can infer that the universe is homogeneous and isotropic on the largest scales, meaning it looks roughly the same everywhere. These patterns suggest that the cosmic web is just a slice of a much larger, possibly boundless universe. If the same structures continue beyond what we can see, space might stretch endlessly, filled with filaments, clusters, and voids, far beyond the reach of our telescopes. Advanced surveys have also uncovered unexpected features in the cosmic web. Some filaments are longer and more massive than anticipated. Some voids are emptier than models predicted, and clusters sometimes appear aligned in ways that challenge simple simulations. These surprises hint at new physics or subtleties in cosmic evolution, showing that the large-scale structure is not just a map, but a detective story with clues about dark matter, dark energy, and the forces shaping the universe. Another fascinating development is the combination of galaxy mapping with gravitational lensing. Massive clusters bend the light of galaxies behind them, creating distortions in their appearance. By measuring these distortions across the cosmic web, astronomers can map the distribution of dark matter, even where no galaxies exist. This technique has confirmed that filaments are threaded with unseen mass, linking clusters and shaping the cosmic landscape in ways invisible to ordinary telescopes. As the cosmic web continues to be mapped in greater detail, we are also beginning to connect large-scale structure to the earliest moments of the universe. Tiny fluctuations in the CMB set the stage for the formation of filaments and clusters. Observing the cosmic web is like seeing the results of billions of years of cosmic evolution, tracing the growth of matter from subtle ripples in a hot plasma to the grand scaffolding of galaxies. Each filament, cluster, and void is a testament to the interplay of gravity, dark matter, and expansion, a living record of the universe's history written across unimaginable distances. The largest surveys today are pushing into ever greater volumes of space, mapping hundreds of millions of galaxies and stretching the 3D map to unprecedented scales. By doing this, scientists can detect patterns that reveal not just local structure, but the overall shape and extent of the universe. Are we looking at a region of an infinite cosmos? Are there boundaries beyond our horizon? While we cannot directly see past the limits of our observation, the distribution and uniformity of matter give indirect clues, letting cosmologists infer that the universe might be far larger than what we can measure, potentially infinite. The cosmic web also provides context for our own place in the universe. Our galaxy, the Milky Way, sits in a relatively quiet neighborhood, part of the local group of galaxies, which itself is connected to the Laniakea supercluster, a massive region spanning over 500 million light-years. From this perspective, we are tiny actors in a vast cosmic stage, woven into filaments that stretch across the observable universe. Every cluster, filament, and void tells us something about the forces that shaped our neighborhood, and about the invisible threads holding it together. Inflation theory and the infinite universe. Imagine the universe in its first fractions of a second, hotter than anything we can even picture, smaller than an atom, and expanding faster than the speed of light. This is the stage where the universe's story takes a dramatic twist, the moment called inflation. For decades, scientists had wrestled with puzzles in the Big Bang theory. Why does the universe look the same in every direction, even in regions that couldn't have been in contact? Why does space seem so flat, as if someone had stretched it perfectly smooth? The answers to these mysteries came in the 1980s with the idea of cosmic inflation, a mind-bending episode when space itself expanded faster than anything, stretching tiny quantum fluctuations into the vast structures we see today. Inflation isn't just a faster Big Bang. It is a separate, extraordinary phase. In the first tiny fraction of a second after the initial singularity, the universe didn't just expand. It ballooned exponentially, doubling in size over and over, many times in a fraction of a heartbeat. During this period, regions of space that were once unimaginably small grew to encompass volumes billions of light-years across. This solves two major problems in cosmology: the horizon problem and the flatness problem. The horizon problem asks, why does the universe look so uniform in all directions? Light can only travel so far in a given amount of time, so regions separated by billions of light-years shouldn't have known about each other in the early universe. Yet the cosmic microwave background shows uniformity to 1 part in 100,000. Inflation explains this by stretching a tiny uniform patch of space so dramatically that it now spans the observable universe. What we see as vast and homogeneous today was once small enough to share the same conditions, smoothing out differences before expansion blew it up across the cosmos. The flatness problem is equally striking. Measurements show that the universe is nearly perfectly flat. Without inflation, achieving this degree of flatness would require incredibly precise conditions at the beginning, a cosmic coincidence so improbable that it troubled physicists. Inflation solves this naturally. As space stretches exponentially, any initial curvature is flattened out, like blowing up a balloon until its surface appears flat, no matter where you stand. This explains why the universe looks geometrically smooth on the largest scales, without requiring finely tuned initial conditions. Inflation also provides a mechanism for creating the universe's large-scale structure. Even during this violent, rapid expansion, quantum fluctuations, tiny random variations in energy at the smallest scales, were stretched along with space. These minuscule variations became seeds for galaxies, clusters, and the cosmic web. Where the energy was slightly higher, matter would eventually clump together. Where it was slightly lower, voids formed. The filaments, clusters, and voids we mapped in the Sloan Digital Sky Survey and other galaxy surveys today are the amplified echoes of quantum jitters that occurred in the first trillionths of a second. In this sense, inflation bridges the microscopic world of quantum mechanics with the macroscopic universe, showing how the tiniest fluctuations became the vast structures we see across billions of light-years. Perhaps the most mind-bending consequence of inflation is the possibility of infinite space. If the exponential stretching continues, there's no natural boundary to where it stops. The observable universe, the part we can see, is just a tiny patch within a much larger, potentially unbounded cosmos. Beyond the horizon, space may continue endlessly, forming regions like ours that are causally disconnected but follow the same physical laws. This idea of a universe without edges transforms our understanding of size in a way that is almost impossible to visualize. We live in a universe that might have no edge at all, where galaxies, filaments, and voids extend infinitely in every direction. Cosmologists also explore eternal inflation, a scenario where inflation never completely stops. While certain regions of space cool and form galaxies, other regions continue to inflate, generating new bubble universes. Each bubble could have its own distinct properties, laws of physics, or rates of expansion. We may exist in one of these bubbles, unaware of the others because the space between them expands faster than light, keeping them forever beyond our reach. This is not philosophy or science fiction. It's a scientific prediction derived from equations of inflation. Eternal inflation shows that what we see may be just one patch in a vast self-replicating multiverse where universes continuously spawn across infinite cosmic space. Inflation also connects beautifully with the cosmic microwave background. The tiny fluctuations we observe in the CMB are exactly what inflation predicts, nearly uniform, with slight variations that match the scale and pattern expected from quantum fluctuations stretched during inflation. Satellites like Planck have measured these fluctuations with incredible precision, confirming the fingerprints of inflation and providing strong evidence that this rapid early expansion really happened. By analyzing the size and distribution of these anisotropies, scientists can reconstruct the universe's growth and confirm that the large-scale structures we see today, clusters, filaments, and voids, have their origins in the inflationary epoch. Inflation also shows cosmic possibilities. It doesn't just explain the universe's smoothness and flatness, it predicts patterns and structures that we can test with observations. For example, inflation models suggest the existence of primordial gravitational waves, ripples in space-time generated during the rapid expansion. Detecting these waves would be like listening to the heartbeat of the early universe, confirming how inflation unfolded in the first fractions of a second. Scientists are designing experiments to find these subtle signals, from ground-based telescopes to satellites scanning the polarization of the CMB, hoping to catch a whisper from the universe's explosive beginning. Inflation theory and the infinite universe. One of the clearest imprints of inflation comes from quantum fluctuations amplified to cosmic scales. Tiny variations in energy density from the very first fractions of a second become the seeds for galaxies and clusters. These initial fluctuations are stretched across space, forming regions slightly denser than their surroundings, which pull in more matter through gravity. Other regions become slightly less dense, forming cosmic voids. The patterns of clustering, the sizes of filaments, and the shapes of superclusters we map today are directly linked to those infinitesimal quantum jitters during inflation. Without that early exponential stretching, the universe would be far more uniform and featureless, lacking the intricate cosmic web we see. The cosmic microwave background, CMB, provides a direct window into these fluctuations. Satellites like Planck and WMAP measure tiny temperature differences across the sky, revealing the statistical patterns predicted by inflationary models. Some spots are slightly hotter, others slightly cooler, tracing density differences of 1 part in 100,000. These patterns are not random. Their scale, distribution, and alignment match what inflation predicts for a rapidly expanding, near-uniform early universe. By analyzing the angular power spectrum of these fluctuations, cosmologists can measure properties like the universe's flatness, the amount of dark matter, and even the influence of dark energy. Every point in the CMB sky carries a story from the inflationary epoch, connecting the smallest quantum jitters to structures billions of light-years across. Inflation also predicts primordial gravitational waves, subtle ripples in space-time generated during the explosive expansion. These waves stretch and squeeze the fabric of the universe as they propagate, leaving tiny imprints on the polarization of the CMB. Detecting these signals is like listening to the echo of the universe's first heartbeat. While incredibly faint, these waves carry information about the energy scale of inflation and could provide direct evidence for how space grew exponentially in a fraction of a second. Experiments are underway around the world, scanning the sky for these delicate signatures, hoping to confirm what inflationary theory has long predicted. Another key feature of inflation is the possibility of eternal inflation, where some regions of space continue to expand even as others stop inflating and form bubble universes. In this scenario, our observable universe is just one bubble in a vast multiverse. Each bubble could have slightly different properties, such as variations in the strengths of fundamental forces or the abundance of matter and energy. The inflationary mechanism itself naturally generates these bubbles, creating pockets of space where galaxies, stars, and potentially life can form, while other regions expand at nearly the speed of light, forever unreachable. Eternal inflation is derived from well-tested physical equations, not speculation. It is a consequence of the energy landscape of the early universe, showing how the multiverse emerges from the physics of inflation. The structure of these inflationary bubbles is reflected in the distribution of matter and galaxies we observe. In large galaxy surveys, clustering patterns, filament lengths, and void sizes carry subtle hints about the initial conditions of inflation. For example, the spacing of clusters and the scale of baryon acoustic oscillations are consistent with the way inflation would amplify tiny fluctuations and imprint a characteristic scale on the universe. These patterns allow scientists to test inflation quantitatively, connecting the theory of the first moments to the observable universe today. Inflation also has implications for the concept of infinity. If inflation is eternal in some regions, space could extend indefinitely. While we can only see a finite portion, the observable universe, there may be an unending network of bubbles beyond our horizon. Each bubble would be causally disconnected, expanding faster than light relative to us, making them forever invisible. Even though we cannot directly observe them, their existence is predicted by the same physical laws that explain inflation and structure formation, suggesting that infinity is not just a mathematical idea, but a natural consequence of cosmic physics. The connection between quantum mechanics and inflation becomes even more profound when considering fluctuations that affect large-scale structure. Tiny variations in energy density are magnified during inflation, turning microscopic effects into features billions of light-years across. This bridges the smallest scales of reality with the grandest cosmic scales, showing that the universe's largest patterns, the web of galaxies, the distribution of clusters, the emptiness of voids, originate in the quantum foam of the earliest moments. Inflation provides a mechanism for these quantum effects to become macroscopic, linking the laws of the very small with the structure of the very large. Modern simulations of cosmic evolution confirm this connection. Starting with initial conditions derived from inflation, computer models can reproduce the cosmic web, clusters forming along filaments, voids expanding, and galaxies flowing along gravity's invisible scaffolding. Comparing these simulations with galaxy surveys and CMB measurements allows scientists to refine the parameters of inflation, testing how rapid the expansion was, how long it lasted, and how quantum fluctuations seeded the patterns we see today. These studies show that inflation is not a vague idea. It is a predictive theory that explains why the universe has the structure it does and provides a framework for testing the limits of space itself. Observations also probe the boundaries of our observable patch. Because inflation stretches space faster than light, regions that were once close can now lie beyond our horizon. This means that the universe we see may be just a tiny fraction of a far larger reality. The patterns in the CMB, the clustering of galaxies, and the scale of superclusters all hint at an underlying order and uniformity that extends far beyond our ability to observe directly. Inflation allows us to connect what we can see with what may exist beyond, providing a glimpse into the immense, possibly infinite architecture of the cosmos. Inflation also has practical consequences for how we understand cosmology today. By providing a mechanism for flatness and homogeneity, it explains why dark matter and dark energy dominate cosmic behavior, why structures form where they do, and why the universe behaves predictably on the largest scales. It gives us a framework for testing new physics, from quantum gravity to early universe energy landscapes, and provides a roadmap for experiments designed to probe the origins of the universe itself. Through all of this, the universe reveals itself as a dynamic, expanding, and potentially infinite space. Inflation ties together quantum mechanics, cosmology, and observational astronomy, showing that the earliest moments have left fingerprints across billions of light years. Every galaxy, cluster, filament, and void is a product of those first fleeting fractions of a second, a testament to the explosive power of space itself, and a clue to the vastness that may lie beyond our sight. Methods of measuring the universe. Measuring the universe doesn't stop with mapping galaxies and finding distances. It's also about understanding how the universe behaves, what drives its expansion, and how its vast structure fits together. The methods astronomers use work together, like pieces of a giant cosmic puzzle, revealing both the visible universe and the invisible forces shaping it. One of the most fascinating ways we study the universe is through how different methods cross-check each other. Redshift surveys show us how galaxies move and where they are in 3 dimensions. Standard candles like Cepheids and Type Ia supernovae give us absolute distances. When these are combined with baryon acoustic oscillations, astronomers get a cosmic ruler that spans billions of light years. This ruler lets them measure the universe's expansion at different times in history, showing not just how far galaxies are, but how far space itself has stretched. These techniques also reveal the subtle influence of dark energy, the mysterious force driving the acceleration of the universe's expansion. By comparing distances measured using standard candles with the clustering patterns from BAO, scientists can see how expansion has changed over time. The result is a dynamic picture of the universe: galaxies racing apart, filaments stretching, and voids widening, all under the invisible push of dark energy. Observing these effects requires extreme precision because the differences are tiny on human scales, but enormous across billions of light-years. Another powerful tool comes from gravitational lensing, which allows astronomers to map both visible and invisible matter in ways no other method can. Light from distant galaxies is bent by massive clusters along its path, distorting their shapes. By measuring these distortions statistically, scientists can map the total mass distribution, including dark matter, across huge regions of space. Lensing works on multiple scales. Weak lensing detects subtle distortions across millions of galaxies to map the cosmic web, while strong lensing produces dramatic arcs and multiple images of background galaxies. Both provide essential measurements of mass, distance, and geometry, helping refine our understanding of the universe's expansion and large-scale structure. Precision cosmology also relies on key numbers that anchor our maps. The observable universe stretches about 93 billion light-years across, a number calculated from the combination of redshift, expansion rates, and cosmic geometry. Within this enormous volume, astronomers measure distances with remarkable accuracy, linking nearby Cepheids with far-off supernovae and the clustering of galaxies measured through BO. Every method improves the others. Standard candles calibrate redshift surveys, BAO provides independent checks on expansion, and gravitational lensing confirms mass distributions. Together, they create a high-resolution three-dimensional map of the cosmos, showing not just where galaxies are, but how the universe behaves over billions of years. These measurements also help track cosmic history. By looking at galaxies at different distances, astronomers see the universe as it was at different times. Farther galaxies appear as they were billions of years ago, when the universe was younger and structures were forming. Comparing these observations with local galaxies shows how clusters grew, how filaments stretched, and how voids expanded. Each technique, redshift, standard candles, BAO, lensing, offers a different perspective, combining to form a timeline of cosmic evolution that stretches from the first few 100,000 years after the Big Bang to today. Modern telescopes and surveys make this work possible on a scale that would have been unimaginable decades ago. Massive projects like the Dark Energy Survey, the Euclid mission, and the next generation of telescopes will map billions of galaxies, measure distances with unprecedented precision, and even detect subtle distortions caused by dark matter. These efforts allow astronomers to refine the Hubble constant, test models of cosmic expansion, and investigate whether the universe is finite, infinite, or curved in ways that are only detectable across the largest scales. Even the tiniest details matter. The spacing between galaxy clusters, the alignment of filaments, and the density of voids all carry information about the universe's expansion and the forces shaping it. Baryon acoustic oscillations provide a cosmic yardstick, allowing us to measure distances with accuracy that stretches across billions of light-years. Gravitational lensing fills in the invisible mass that we cannot see with light, and standard candles ensure that the cosmic distances are anchored in physical measurements. Redshift surveys provide the framework, showing the positions and motion of galaxies over immense volumes of space. Together, these methods allow cosmologists to decode the universe, translating faint signals into a coherent map of space and time. As these techniques improve, we are not only refining distances and expansion rates, but also testing the limits of what we can observe. The observable universe is defined by how far light has traveled since the Big Bang, but by understanding expansion and mapping mass distributions, we can infer properties of regions beyond our view. Patterns in galaxy clustering, BAO scales, and lensing distortions hint at structures and forces beyond our observational horizon, allowing us to explore the unseen boundaries of space indirectly. Ultimately, these measurement methods are about precision and connection. Each galaxy measured, each supernova analyzed, and each distortion in light from a distant cluster provides data points that tie the cosmos together. By combining redshift surveys, standard candles, BAO, and gravitational lensing, astronomers can construct a detailed, evolving map of the universe, showing not just where galaxies are, but how space itself stretches, how structures form, and how unseen forces like dark matter and dark energy shape the cosmos on the largest scales. This is the frontier of cosmic measurement, pushing ever farther, refining every number, and connecting the tiniest fluctuations in the early universe with the massive structures we see today. Limits of measurement and uncertainty. Try to imagine standing on a cliff, looking out over an endless ocean. You can see the waves crashing, the horizon stretching as far as the eye can reach, but you know the ocean continues beyond what you can see. That's what the universe feels like when we measure it. No matter how powerful our telescopes, how precise our measurements, there is a cosmic horizon, a limit to how far we can see, defined not by laziness or technology, but by the physics of light and time itself. The universe is about 13.8 billion years old, so light from farther away hasn't had enough time to reach us. Even though space has been expanding while the light travels, stretching it across billions of light years, there is a boundary, the edge of our observable universe, beyond which information has yet to arrive, and we may never see it. This cosmic horizon isn't just a simple distance, it is a moving target because the universe is expanding. As light travels toward us, the space it passes through stretches, meaning that galaxies we see today are much farther than the distance light traveled. The observable universe spans roughly 93 billion light-years across, yet that is just what we can detect. Beyond that, galaxies and clusters exist, but their light will never reach us, at least not within the lifespan of the universe as we know it. Measuring beyond this horizon is physically impossible, a hard limit imposed by the speed of light and the finite age of the universe. Even inside the observable patch, our measurements are influenced by dark energy, the mysterious force accelerating the expansion of space. Galaxies that were once within view will eventually recede faster than light due to this acceleration, slipping beyond our horizon forever. In a sense, the universe is constantly hiding parts of itself from us. Each observation we make is like catching a snapshot of a moving painting, only able to see fragments, while the rest drifts beyond our reach. The interplay between the cosmic horizon and dark energy defines the limits of what we can know and see. Adding another layer of complexity is the Hubble tension, the discrepancy between different methods of measuring the universe's expansion rate. Using Cepheids and type Ia supernovae, astronomers get one number for the Hubble constant. Using cosmic microwave background data, they get a slightly different number. The difference is small in human terms, but massive on cosmic scales, affecting calculations of distances, the age of the universe, and the ultimate fate of structures at the edges of our observable horizon. It highlights that even the techniques we trust the most carry uncertainties, and sometimes they disagree in ways that force scientists to rethink models, adjust measurements, and refine methods. Beyond measurement discrepancies, there's the profound question of infinity. If space continues beyond the observable universe, can we ever measure it? The short answer, not directly. The observable universe is like a bubble, with a finite size, inside a potentially infinite cosmos. While we can extrapolate properties of the unobservable region based on physics, models, and patterns inside the observable part, we will never have direct confirmation. The universe may be open, flat, or closed, extending endlessly in one or more directions, or curving back on itself in ways that only become noticeable on scales far beyond what we can detect. This is where precision cosmology meets imagination. We can model infinity mathematically, test predictions, but we cannot physically measure beyond the cosmic horizon. The distinction between the observable universe and the actual universe is crucial. When we talk about the universe as a whole, we often assume it is uniform, that structures beyond the observable patch follow the same laws and distribution as those we see. But this is an assumption, grounded in the cosmological principle, not a fact. The universe beyond what we can detect may look the same, or it may hold surprises, regions denser or emptier, structures larger than we can imagine, or variations in fundamental physics. The observable universe is a fraction of the actual universe, a lens through which we interpret the whole, yet always limited by light, expansion, and cosmic time. Even with all these limits, astronomers have found clever ways to push measurements to the edge of what is observable. Redshift surveys, standard candles, gravitational lensing, and baryon acoustic oscillations allow scientists to measure distances, expansion rates, and mass distributions with remarkable precision. But no matter how sophisticated, these methods are constrained by fundamental physics. Light can't travel faster than its speed limit, and the universe is expanding in a way that carries some regions beyond reach. The edge of measurement is not technological, it is built into the structure of the cosmos itself. Looking at uncertainty from another angle, the act of measuring the universe always carries errors and limitations. Instruments are sensitive to noise, calibration requires assumptions, and the further we look, the fainter the signals become. Observing a galaxy 10 billion light-years away is not just looking far, it's seeing light stretched, dimmed, and altered by everything it has passed through. Dust, gravitational lensing, cosmic expansion, and local motions all affect the signal. To extract meaningful data, astronomers must account for all these factors, modeling the physics of space, matter, and radiation across time. Each measurement becomes a combination of observation and interpretation, a dance between the universe's signals and our ability to read them. The limits of measurement also tie into our understanding of time itself. Because light travels at a finite speed, looking far away means looking back in time. The farther we see, the younger the universe appears. But there is a point where distances and expansion rates mean light emitted from galaxies will never reach us, meaning entire regions remain forever hidden in the past, beyond any possible observation. This creates a natural boundary for knowledge, where physics, light, and time combine to define the ultimate horizon of what we can measure. Cosmic acceleration, measurement errors, and the fundamental speed of light all reinforce that uncertainty is woven into cosmology. Even the most advanced surveys and telescopes cannot escape the limits imposed by the universe itself. Yet, by combining methods, redshift, standard candles, BAO, lensing, scientists can reduce uncertainty, cross-check results, and extract the maximum possible information from the observable bubble. Every improvement, every new telescope, every longer survey pushes the boundaries a little further, refining our understanding of cosmic distances, expansion, and structure. The universe is vast, and a measurement is always a balance between what is visible, what is predictable, and what lies forever beyond. Observing the universe is not just about mapping galaxies. It is about understanding how much of the universe we can know, how far information travels, and where the limits are written into the very physics of space-time. Each observation reminds us of the edge, the cosmic horizon, the accelerating expansion, the tension between different measurements, and challenges us to measure ever more precisely, even as the universe continues to stretch its secrets out of reach. Precision mapping of cosmic structures. Even as the cosmic horizon limits what we can see, astronomers are finding creative ways to probe what lies beyond, not by seeing it directly, but by studying the effects it leaves on the universe we can observe. One of the most powerful tools in this effort is precision mapping of cosmic structures. Galaxies, clusters, and filaments are not scattered randomly. They trace the underlying distribution of mass and energy, including dark matter, and they carry subtle fingerprints of the universe's earliest moments. By carefully analyzing these structures, scientists can infer properties of regions we cannot see, giving indirect glimpses of the universe beyond our horizon. Gravitational lensing plays a major role here. When light from distant galaxies passes massive structures on its way to us, it bends, creating distortions. These distortions tell us about the mass distribution in foreground regions, but they also reveal cumulative effects from mass in regions that lie far beyond direct observation. In essence, lensing allows us to feel the presence of what we cannot see. Patterns in weak lensing across billions of galaxies create maps of invisible matter stretching far into the universe, hinting at the vast continuous web that may extend indefinitely. Alongside lensing, baryon acoustic oscillations, BAO, provide another method to peek beyond what's visible. BAO sets a standard cosmic scale imprinted in the distribution of galaxies, remnants of sound waves traveling through the early universe's plasma. By measuring how this scale appears at different distances, astronomers can test how space itself has expanded and even speculate on conditions in areas too distant for light to reach us. The oscillation patterns act like a ruler stretching across billions of light years, connecting our observable universe to the invisible fabric of the cosmos. Yet even with these clever methods, the question of infinity remains. If space extends endlessly, can we ever truly measure it? Direct measurement is impossible. Light from infinitely distant regions will never arrive. But scientists use models grounded in physical laws to estimate what may lie beyond. Patterns in galaxy clustering, CMB measurements, and expansion rates all suggest uniformity on large scales, giving evidence that the universe may be far larger than what we can see, potentially infinite. Still, each inference comes with uncertainty, and cosmologists must always acknowledge the difference between what is observable and what might exist. This is where the Hubble tension adds another layer of complexity. Different ways of measuring the expansion rate using nearby standard candles versus the cosmic microwave background give slightly different values. The tension is small in percentage terms, but large enough to affect estimates of distances and timing for far-off galaxies. When projecting into regions beyond our horizon, these small discrepancies can become significant, changing our estimates of when light from certain regions might ever reach us, or even whether some structures are effectively out of causal contact forever. It is a reminder that uncertainty scales with distance in the universe, and the farther we try to look, the more fundamental limits of measurement come into play. Another way astronomers handle uncertainty is by combining multiple measurement techniques. No single method is perfect. Each has strengths, weaknesses, and systematic errors. Redshift surveys map positions and velocities. Standard candles provide absolute distances. BAO gives a cosmic ruler, and gravitational lensing reveals invisible mass. Together, they form a cross-verified map, reducing error and increasing confidence. Even so, the further out we go, the more assumptions are required, such as the homogeneity of unobservable regions, or the constancy of dark energy over time. These assumptions are grounded in the best available physics, but they highlight that certainty fades as we approach the edges of what light and time allow us to see. Technology continues to push the limits of what we can measure. Telescopes like James Webb, surveys like DESI, and upcoming space missions are extending redshift measurements, refining supernova distances, and mapping lensing patterns across vast swathes of the sky. These advances allow scientists to see fainter galaxies, detect more subtle distortions, and measure the expansion of space with greater precision than ever before. Yet even with the best technology, the cosmic horizon is unavoidable. There will always be regions beyond reach, where light has not arrived, and any measurement becomes impossible. Interestingly, some methods allow indirect glimpses of the universe's farthest reaches without seeing the galaxies themselves. For example, the cosmic microwave background, CMB, carries information from the edge of what was once visible, the time when the universe became transparent, about 380,000 years after the Big Bang. Tiny temperature fluctuations in the CMB reflect density variations that later became galaxies and clusters. By analyzing these patterns, astronomers can infer properties of the universe on scales far larger than individual galaxies, effectively extending our understanding into regions we will never observe directly. At the frontier of measurement lies a fascinating tension between practical observation and theoretical inference. While we can only see the observable universe, physics allows us to model what might exist beyond it. Inflationary theory, combined with measurements of large-scale structure, suggests that space could continue endlessly, with similar patterns repeating far beyond our horizon. Still, we cannot directly test these predictions. Instead, scientists rely on the consistency of physical laws, indirect signals like gravitational lensing and BAO, and the statistical properties of observable structures to extrapolate to the unknown. This is measurement pushed to its ultimate limits, precision constrained not by instruments, but by the universe itself. Even uncertainty teaches us something profound. The very act of measuring the universe highlights that our knowledge is finite, limited by light speed, cosmic expansion, and the laws of physics. Yet it also shows that the universe is coherent, predictable, and structured, allowing scientists to reach far beyond what is immediately visible. Every new survey, every refined measurement, every subtle lensing map extends the horizon of understanding, inching closer to answering questions about size, structure, and infinity, even while some parts remain forever out of reach. Cutting-edge research and future prospects. Imagine pointing a telescope so powerful that it doesn't just see distant galaxies. It looks back in time, glimpsing the first moments of the universe when stars and galaxies were just forming. That is the promise of the James Webb Space Telescope, JWST, humanity's most advanced eye in space. Unlike its predecessor Hubble, which mostly observes visible and near-infrared light, JWST peers deep into the infrared spectrum, letting us see through cosmic dust and detect the faint glow of galaxies that formed less than 1 billion years after the Big Bang. Every image from JWST is not just a picture, it's a time machine, revealing the universe's early chapters with unprecedented clarity. By studying these primordial galaxies, astronomers can refine estimates of how quickly structures formed, how matter clustered, and how the universe expanded in its first few 100 million years. JWST's capabilities are transforming cosmology. It can detect tiny fluctuations in early galaxies, measure the light from the earliest stars, and even identify chemical fingerprints in distant atmospheres. This is crucial because every new galaxy observed at these early epochs acts as a marker, helping scientists test predictions from inflation, map the growth of cosmic structures, and refine measurements of the universe's geometry. The shape, size, and expansion history of the cosmos are not just abstract concepts. They are encoded in the distribution and brightness of these galaxies. And JWST gives us a clearer view than ever before. But JWST is only one piece of the puzzle. Upcoming missions like Euclid and the Rubin Observatory are poised to expand our understanding in ways that go beyond looking at individual galaxies. Euclid will map the large-scale structure of the universe with extreme precision, surveying billions of galaxies across 1/3 of the sky. Its goal is to measure how dark energy drives the expansion of space and to detect subtle distortions in light caused by gravitational lensing, providing insights into the distribution of dark matter. Meanwhile, the Rubin Observatory, with its legacy survey of space and time, LSST, will repeatedly scan the sky, detecting transient events like supernova and tracking changes in millions of galaxies. Together, these observatories will create dynamic, evolving maps of the universe, linking the positions of galaxies, the effects of dark matter, and the expansion of space over time. Future measurements also rely on new cosmic rulers, tools that go beyond light from stars and galaxies. Gravitational waves, ripples in space-time caused by massive cosmic events, are opening a new window into the universe. Detecting these waves allows scientists to measure distances to cataclysmic events, like merging black holes or neutron stars, independently of light-based methods. They can act as standard sirens, providing an alternative way to test the universe's expansion rate and cross-check distances measured by supernovae or redshift surveys. Similarly, the cosmic neutrino background, a relic from the early universe, offers another potential ruler. While neutrinos interact extremely weakly with matter, measuring their faint signatures could give information about the universe's density and growth in the first seconds after the Big Bang, refining our understanding of cosmic inflation and early expansion. Another exciting frontier is the 21-centimeter hydrogen line emitted by neutral hydrogen atoms in the early universe. By detecting this faint radio signal across vast distances, astronomers can map the distribution of matter before galaxies even formed. This technique promises a three-dimensional view of the cosmic web at its infancy, offering an unprecedented look at how structures evolved from primordial fluctuations to the vast filaments, clusters, and voids we see today. Combining this with JWST and Euclid observations could dramatically sharpen our measurements of the universe's geometry, expansion rate, and ultimate size. All of these new methods are not just incremental improvements, they represent a paradigm shift in cosmology. Instead of relying solely on traditional optical telescopes and standard candles, astronomers can now probe the universe across multiple wavelengths, signals, and phenomena. Gravitational waves, neutrinos, radio signals, and infrared light together create a multi-messenger view, allowing cross-checks and precision measurements previously impossible. By combining these data, scientists can refine the shape of space, test theories of inflation, and explore whether the universe is truly infinite or has subtle curvature that only becomes apparent on the largest scales. What makes this era of observation even more thrilling is the scale and depth of surveys now possible. JWST can see individual galaxies billions of light-years away. Euclid can map billions of galaxies across cosmic filaments, and Rubin will track dynamic changes over the entire sky. The combination allows scientists not only to measure distances, but also to understand the growth of structure over time, connecting the earliest galaxies to the vast clusters and filaments we see today. Each observation contributes to a cosmic map that is both spatial and temporal, charting billions of years of history and offering insights into the universe's expansion, composition, and hidden forces. At the same time, these advanced tools help tackle the universe's biggest mysteries. Dark energy, which accelerates expansion, and dark matter, which shapes the cosmic web invisibly, remain elusive. Observatories like Euclid and Rubin, combined with JWST's deep field capabilities, provide the first chance to measure these forces directly by observing their influence on galaxies, clusters, and gravitational lensing patterns. These observations can refine estimates of the universe's age, the Hubble constant, and the geometry of space itself, helping cosmologists understand whether the universe is flat, curved, or infinite. The future of measuring the cosmos also lies in unexplored methods, from neutrino detection to gravitational wave observatories far beyond LIGO, and radio telescopes tuned to the faint signals of primordial hydrogen. These new rulers complement traditional distance measurements, offering ways to probe cosmic epochs beyond the reach of light. By combining them with JWST, Euclid, Rubin, and other upcoming missions, astronomers are building a toolkit capable of mapping the universe from the first seconds after the Big Bang to its farthest observable edges, refining our understanding of expansion, structure, and cosmic limits. The exciting reality is that every observation builds on the last, with each mission revealing new details and challenging existing assumptions. JWST's infrared deep fields uncover galaxies we could not see before. Euclid's wide surveys connect those galaxies into a large-scale structure. Rubin's time-lapse view captures evolution in action. Gravitational waves and neutrino backgrounds provide independent checks on expansion. Together, they form a multi-dimensional, multi-messenger approach, pushing cosmology to a level of precision and reach that was science fiction just decades ago. how these future missions could completely transform our understanding of the universe. Looking ahead, the next decades of cosmic exploration are about more than just seeing farther. They're about understanding the universe in ways we could only imagine a few years ago. The combination of JWST, Euclid, Rubin Observatory, and next-generation instruments will give us not just snapshots, but deep, interconnected movies of the cosmos, letting us trace the evolution of galaxies, clusters, and filaments across billions of years. Every observation will feed into a larger picture, revealing how structures form, how dark energy accelerates expansion, and how invisible matter sculpts the universe from behind the scenes. One of the most exciting prospects lies in the use of gravitational waves as a cosmic ruler. These ripples in space-time are not just signals of spectacular events like black hole mergers. They carry information about distances and cosmic expansion that is entirely independent of light-based measurements. With future observatories like LISA, Laser Interferometer Space Antenna, and even more sensitive ground-based detectors, we will be able to detect gravitational waves from sources billions of light-years away, allowing us to measure expansion rates and distances at scales previously unreachable. This is crucial for resolving long-standing questions like the Hubble tension, and it may reveal subtle features of the universe that light alone cannot show. Meanwhile, the neutrino background offers another window into the early universe. These nearly massless, elusive particles streamed freely through space just seconds after the Big Bang, long before light could escape. Detecting and mapping them would give cosmologists a direct probe of the universe's infancy, revealing density fluctuations, expansion rates, and possibly hints of physics beyond the standard model. Although the neutrino background is incredibly challenging to observe, future experiments and detector arrays may finally make it possible, giving us a new ruler for measuring cosmic distances and structures, complementary to galaxies, supernovae, and BAO. The 21-centimeter hydrogen line remains another frontier. By mapping neutral hydrogen across the universe, astronomers can create a three-dimensional picture of the cosmic web in its earlier stages, long before stars lit up the universe. This allows us to see the first filaments and voids forming, showing how matter clustered under the influence of gravity and dark energy. Unlike galaxies, which appear only after stars ignite, hydrogen mapping gives a glimpse of the pristine structure of space itself, offering a ruler that spans from the very beginning of cosmic history to the formation of visible galaxies. When combined with JWST observations, we get both the seed and the bloom, the scaffolding of the universe and the galaxies that grew upon it. Future missions will also refine our understanding of dark energy and dark matter, the invisible forces shaping the cosmos. Euclid and Rubin will map billions of galaxies to detect subtle distortions in shape caused by dark matter, while large surveys track how expansion has changed over time under the influence of dark energy. With more precise measurements, we may uncover whether dark energy is constant or if it changes over time, potentially altering our predictions for the fate of the universe. Similarly, mapping the distribution of dark matter with ever greater resolution could reveal unexpected structures, regions that challenge current cosmological models, and push the limits of what we know about the universe's geometry and composition. Also, new computational and simulation techniques will play a major role in future measurements. Observations are only one part of the puzzle. Modeling how galaxies evolve, how dark matter interacts, and how large-scale structures form allows scientists to test theories at scales beyond direct observation. High-performance simulations combined with JWST, Euclid, and Rubin data can extrapolate from the observable universe to the unobservable, helping to predict what might lie beyond the cosmic horizon. These virtual universes act as laboratories where hypotheses about infinity, cosmic curvature, and the interplay of matter and energy can be explored and tested. Another transformative development is multi-messenger cosmology, where astronomers combine light, gravitational waves, neutrinos, and other signals to probe the same event or structure from different angles. A single galaxy cluster, for instance, can be mapped in optical light, infrared light, X-rays, gravitational lensing, and possibly even neutrino flux. This approach provides a three-dimensional, multi-dimensional view of the universe, drastically reducing uncertainties and revealing details that no single observation could show. The synergy of these methods is a glimpse of how precision cosmology will reach new heights, letting us understand the universe not just as a static picture, but as a dynamic, evolving, multi-layered reality. With all these tools combined, we are moving toward the ability to measure the universe with unprecedented precision. The shape, size, and curvature of space, once only theorized, may finally be quantified with confidence. We may detect subtle deviations from flatness, confirm the predictions of inflation, or uncover new surprises hidden in the behavior of dark energy. Observing galaxies in the first billion years, mapping hydrogen before stars formed, detecting gravitational waves and neutrinos from cosmic dawn. All of these approaches push the frontier of knowledge, expanding the observable universe and refining our understanding of the actual universe. Ultimately, the next generation of research will push the limits of measurement and imagination together. JWST, Euclid, Rubin, and future experiments are not just collecting data. They are giving humanity the tools to explore the unseen, to measure structures beyond our cosmic horizon, and to refine our understanding of a universe that might be far larger, more complex, and more dynamic than we have ever imagined. By combining every observation, every signal, and every model, we are building the foundation for a new era of cosmology, where the universe is not just seen, but understood in detail across billions of light years, across time, and across invisible forces that shape every corner of space. Even as the edge of the observable universe stretches ever outward, these missions give hope that we can push beyond limits, using creativity, technology, and multi-messenger science to explore regions we may never see directly, and yet understand through their influence on what is visible. The future of cosmic exploration is not just about seeing farther. It is about measuring deeper, connecting the dots, and uncovering the structure and behavior of the universe on scales that were once unimaginable. Every photon captured, every wave detected, and every particle measured brings us closer to a detailed, multi-layered understanding of the cosmos, revealing not just galaxies, but the fundamental forces, expansion, and geometry that define the universe itself. Cosmic perspective. Mind-bending scale. Try to imagine standing on your front yard and looking up at the night sky. The stars sparkle as pinpoints of light, seemingly close, but in reality, each one is hundreds, thousands, or millions of times farther than you can fathom. The nearest star, Proxima Centauri, is over 4 light-years away. That means the light leaving that star today won't reach us until 2030. In human terms, that's unimaginable. In cosmic terms, it's just the beginning of a scale that quickly spins the mind. The universe isn't just big, it is staggeringly vast, with layers of structure stretching from our tiny planet to the edge of the observable cosmos. Start with Earth, our home. It has a diameter of just over 12,700 kilometers, tiny compared to the distances between planets. The solar system, where Earth orbits the Sun, extends out past Neptune to the Oort cloud, a vast shell of icy objects that could stretch halfway to the nearest star. The Sun itself is a medium-sized star, just one of hundreds of billions in the Milky Way. Even this galaxy, our cosmic neighborhood, is vast, roughly 100,000 light-years across. If light could travel the diameter of the Milky Way in a year, it would take a beam of light a full 100,000 years to cross from one edge to the other. That's longer than human civilization has existed, and yet it is just one galaxy in a sea of billions. The Milky Way is part of the Local Group, a cluster of about 50 galaxies bound together by gravity. Among these, the Andromeda Galaxy looms as a massive spiral, heading toward a future collision with the Milky Way in about 4 billion years. Beyond the Local Group lie superclusters. massive conglomerations of galaxies, clusters and filaments stretching millions of light years. The Laniakea supercluster, which includes our Milky Way, contains hundreds of thousands of galaxies and spans over 500 million light years. Visualizing this scale is almost impossible, but it illustrates how tiny our planet really is in the cosmic context, a mere speck in a vast interwoven structure. When we step back further, we reach the observable universe, the bubble of space from which light has had time to reach us since the Big Bang. Its diameter is roughly 93 billion light-years, containing hundreds of billions of galaxies, each with hundreds of billions of stars. To think about it, every star we see, every galaxy we study, is just a glimpse of a larger structure, and light from many regions may never reach us due to the accelerating expansion of space. These distances are so enormous that our normal measures, kilometers, miles, fail completely. Astronomers instead use light years, the distance light travels in a year, or parsecs, roughly 3.26 light years, as a way to grasp cosmic scales. The speed of light becomes a cosmic ruler. Light travels at about 300,000 kilometers per second, fast by any human standard, but slow on the scale of the universe. It takes over 8 minutes for sunlight to reach Earth, 4 years for Proxima Centauri's light, and billions of years for light from the most distant galaxies. When we see a galaxy a billion light-years away, we are seeing it as it was a billion years ago, not as it is today. In this way, observing the universe is like looking back in time, and every distance is also a window into the history of space itself. Understanding these scales isn't just mind-blowing, it is scientifically essential. The distances between galaxies, the velocities of clusters, and the distribution of matter all inform cosmology, the study of the universe's origin, evolution, and fate. Measuring these scales allows scientists to calculate the expansion rate of the universe, test models of dark matter and dark energy, and refine the cosmic map that defines everything from galaxy formation to the ultimate geometry of space. Without an accurate sense of scale, predictions about the universe's future, its shape, and its contents would be impossible. To grasp the mind-bending nature of cosmic distances, consider this. If Earth were the size of a single grain of sand, the Sun would be a basketball several meters away, and the nearest star would be another basketball dozens of kilometers off. The Milky Way would stretch hundreds of thousands of kilometers across, and the nearest galaxy outside our local group would be millions of kilometers distant. Superclusters, filaments, and voids that define the cosmic web would extend far beyond any human experience, placing our home in a context that is simultaneously tiny, fragile, and extraordinary. Observing these structures also requires thinking about light in motion. A distant galaxy we see today may have emitted the light billions of years ago, when the universe was young, smaller, and denser. As that light travels toward us, space itself is expanding, stretching the wavelength of light in a phenomenon called redshift. By measuring redshift, astronomers can determine not only how far away a galaxy is, but also how fast it is receding, providing a direct measurement of the expansion of the universe. This connects the scale of the universe to its dynamic behavior, showing that cosmic distances are not static, but changing continuously as space stretches. Even within the observable universe, the density of matter varies dramatically. Galaxies cluster along filaments in the cosmic web, leaving enormous voids nearly empty of visible matter. These voids can span hundreds of millions of light years, giving a sense of scale that dwarfs human imagination. By mapping clusters, filaments, and voids, astronomers can measure the geometry and growth of the universe, using the structure itself as a yardstick. The farther and larger the structures we observe, the better we can understand the overall size, shape, and possible infinity of space. Visualizing cosmic distances is a challenge for anyone. Light years and parsecs are abstract. Even millions of light years strain the imagination. But by thinking hierarchically, Earth to solar system to Milky Way to local group to superclusters, and beyond to the observable universe, we start to comprehend the sheer scale. Each step up reveals a layer of complexity and vastness, a reminder that while humans are small in physical terms, our ability to measure and understand space bridges enormous scales. The cosmic perspective also changes the way we perceive time. Looking at distant objects means seeing the past. Light from galaxies billions of light years away is ancient light, showing us galaxies when they were much younger, before stars and black holes matured. Observing these objects is like peering into the universe's history book, where every photon carries a story of formation, evolution, and motion. The farther we look, the deeper into time we go, and the larger the scale we measure, linking distance, age, and cosmic structure into a single, continuous understanding. Even scientifically, this perspective matters for practical reasons. Understanding distances allows for the calculation of gravitational influences, predicting the motions of galaxies and clusters. It informs models of galaxy formation, showing how matter clumps over billions of years to create spirals, ellipticals, and massive clusters. Distances also affect energy measurements, such as the brightness of supernovae, which are used to calculate expansion rates and the influence of dark energy. Looking deeper, the cosmic scale starts to feel almost surreal when you think about how astronomers actually measure these distances. Light years are useful, but they are just the beginning. When you want to map billions of galaxies, you need more sophisticated tools. Redshift is one of the most important. As space stretches, light traveling through it stretches too, shifting toward the red end of the spectrum. By measuring this redshift, astronomers can determine not just how far away a galaxy is, but also how fast it's moving away from us. It's like using the universe itself as a giant measuring tape, where every galaxy tells a story of expansion and motion. Redshift surveys take this even further. Imagine scanning the sky to record the position and redshift of millions of galaxies, then plotting them in three-dimensional maps. That's what missions like the Sloan Digital Sky Survey, SDSS, and the 2DF Galaxy Redshift Survey have done. The results are mind-blowing. Galaxies aren't scattered randomly, but form filaments, clusters, and enormous walls, separated by vast empty voids. These patterns show the large-scale structure of the cosmos, giving a sense of distance, scale, and the architecture of space itself. When you look at these maps, it's almost like peering into a giant glowing spiderweb that stretches across billions of light years. Using these surveys, astronomers have developed a way to measure distances to extremely far galaxies. Cepheid variables, the pulsating stars we use as standard candles, are great for nearby galaxies, while Type Ia supernovae shine brightly enough to act as cosmic flashlights across billions of light years. By comparing how bright these objects appear with how bright they truly are, scientists can calculate distance. Combine that with redshift and you start to see not just where galaxies are, but how space itself is stretching over time. Other methods push even further. Baryon acoustic oscillations, or BAO, are ripples frozen into the distribution of matter from the early universe. These cosmic sound waves act like measuring sticks on the largest scales, letting scientists determine the expansion of the universe and infer distances far beyond what we can see directly. Even gravitational lensing, the way massive structures bend light, provides a ruler for mapping invisible matter. By analyzing these subtle distortions, astronomers can measure mass across unimaginable scales and detect structures that are completely invisible in normal light. As we measure these distances, the mind-bending scale becomes even more apparent. Superclusters, like Laniakea, stretch for hundreds of millions of light years, connected by filaments thinner than the gaps they span. The voids in between are almost empty, some hundreds of millions of light years across, giving us an incredible sense of how vast empty space really is. Beyond that lies the observable universe, where light has traveled for 13.8 billion years, but because space itself is expanding, the diameter of what we can see reaches 93 billion light years. Everything we map, measure, and explore fits within this bubble. Yet beyond it, we can only theorize. Visualizing these distances isn't just about numbers. Astronomers often create virtual models, where the Milky Way is a tiny dot. Local group galaxies are dots a few meters away. Superclusters stretch across entire rooms, and the cosmic web extends beyond what we can imagine. These models help put human-scale intuition into a universe that dwarfs everyday experience. Even then, imagining the full scale is nearly impossible. Billions of galaxies, each with billions of stars, each star potentially hosting planets, stretching across incomprehensible distances. It's a scale that defies imagination, but becomes tangible when mapped through data, light, and mathematics. Thinking in terms of time as well as space makes the picture even more dramatic. When we look at a galaxy 10 billion light-years away, we see it as it was 10 billion years ago. That light has traveled across space that was smaller when it started its journey, and has expanded enormously along the way. In that sense, distances in the universe aren't just physical, they're also temporal, connecting space and time into one giant cosmic tapestry. Every measurement of distance is also a measurement of history, letting us see how the universe looked and evolved billions of years before Earth even existed. The cosmic scale also matters scientifically, not just philosophically. Knowing the distances between galaxies and clusters allows scientists to calculate gravitational influences, predict collisions, and understand how structures evolve. Large-scale mapping informs models of dark matter and dark energy, showing how unseen forces shape the universe's architecture. Even predicting the ultimate fate of the cosmos, whether it will expand forever, slow down, or collapse, depends on understanding distances and velocities on a cosmic scale. Technology continues to expand what we can measure. Instruments like the James Webb Space Telescope allow us to see the first galaxies, while surveys like SDSS and upcoming missions map billions of galaxies with incredible precision. Radio telescopes tuned to hydrogen emissions reveal filaments and voids, while gravitational lensing and standard candles provide rulers for measuring beyond what light can reach. These tools don't just increase our understanding, they give us a cosmic perspective, letting us comprehend both the incredible scale and the physical laws that govern it. Step back, and the perspective is mind-blowing. A single planet orbiting a single star in a galaxy that is just one of billions, all moving within a universe that is billions of light-years across. The structures we can observe, the Milky Way, local group, superclusters, filaments, voids, are all part of a dynamic, evolving system. And yet, even with everything we can measure, there is always more beyond the horizon, more distances to stretch, more galaxies to map, and more structures to reveal. Every observation expands the scale, connecting Earth to the vast cosmic web and giving humans a perspective that is at once humbling, exhilarating, and endlessly inspiring. Dark matter and dark energy, invisible forces, shaping the universe. Look up at the night sky, and everything you see, the stars, the planets, the Milky Way, is only a tiny fraction of what's actually out there. The rest? It's invisible, yet it shapes the universe in ways that are completely fundamental. This is the world of dark matter and dark energy, two mysterious forces that dominate the cosmos, controlling the motion of galaxies, the formation of clusters, and the expansion of space itself. Without them, the universe would look completely different. Galaxies might never have formed, cosmic structures wouldn't exist, and the universe could have collapsed or spread apart in ways we can't even imagine. Dark matter is everywhere, but you can't see it. Unlike stars, planets, or gas clouds, it doesn't emit light, absorb light, or interact with electromagnetic forces in any noticeable way. Its presence is inferred entirely through gravity. Galaxies spin in ways that defy the pull of visible matter alone. Stars on the outskirts of galaxies move far faster than expected. There must be something invisible holding them together. That something is dark matter, a ghostly, pervasive substance making up roughly 27% of the universe's total energy. It clumps around galaxies, forms halos, and creates scaffolding for visible matter to gather and form the structures we can see. But dark matter isn't just about holding galaxies together. On the largest scales, it weaves the cosmic web, guiding the formation of filaments, clusters, and superclusters. Without it, galaxies would drift apart before stars and planets could form. Large-scale surveys show patterns that match dark matter's gravitational influence perfectly. Vast sheets of galaxies separated by immense voids, all tracing invisible highways of mass that we cannot see directly. Scientists use gravitational lensing, the bending of light by massive objects, to map where dark matter lies. When light from a distant galaxy bends around an invisible mass, it creates distortions that act like a cosmic fingerprint, revealing the location and shape of the hidden matter. While dark matter holds the universe together, dark energy is pulling it apart. In 1998, astronomers observing distant supernovae discovered something astonishing. The expansion of the universe isn't slowing down under gravity, it's accelerating. There is a mysterious force, now called dark energy, driving galaxies away from each other faster over time. It is even stranger than dark matter, because it doesn't clump or form structures. It's smooth, uniform, and repulsive. Dark energy makes up roughly 68% of the universe, meaning most of the cosmos is composed of stuff we cannot touch, see, or interact with, yet it dominates the universe's evolution. Understanding dark energy isn't just a curiosity. It affects every measurement of distance, every estimate of cosmic age, and every prediction for the universe's future. If dark energy stays constant, the universe will continue expanding forever, stretching galaxies so far apart that the night sky in the distant future will appear almost empty. If it changes over time, the expansion rate could accelerate even more or slow down, altering the cosmic destiny entirely. Astronomers try to measure it by looking at supernovae, galaxy distributions, and gravitational lensing effects on massive scales, all to see how space itself responds over billions of years. One of the most exciting aspects of dark matter and dark energy is that they are completely interwoven with what we can observe. Galaxies, stars, and planets are like glittering islands floating on invisible oceans of mass and energy. Dark matter acts as the ocean floor, shaping how galaxies form and where they gather. Dark energy is the tide, subtly accelerating everything outward. Studying these forces is like piecing together a hidden framework for the entire universe, revealing rules that govern everything from the smallest dwarf galaxy to the largest supercluster. Even more intriguing is how dark matter and dark energy hint at new physics. They don't fit neatly into the standard model of particles and forces. Some theories propose exotic particles like WIMPs, weakly interacting massive particles, or axions, as candidates for dark matter. Others suggest modifications to gravity itself. Dark energy could be a cosmological constant, a property of space, or a dynamic field changing over time. Detecting these directly is one of the greatest challenges in modern physics, requiring detectors buried deep underground, in space, or at the edge of technological sensitivity. Dark matter also leaves its mark on the cosmic microwave background, the afterglow of the Big Bang. Tiny fluctuations in temperature and density from the early universe reveal how matter and radiation interacted, hinting at the invisible scaffolding of dark matter that seeded galaxies. These measurements allow scientists to reconstruct the growth of structure, showing how the universe evolved from a nearly uniform cloud of hot plasma into the intricate web of galaxies we see today. It's like using cosmic archaeology to uncover a hidden world that existed long before stars or planets. The interplay between dark matter and dark energy shapes the ultimate geometry of space. Dark matter's gravitational pull tries to slow expansion locally, forming galaxies and clusters, while dark energy stretches space globally, accelerating expansion. This balance determines whether the universe is flat, open, or curved, and whether it could be infinite or finite. Observations of galaxy clustering, gravitational lensing, and supernova distances all feed into our understanding of this cosmic tug-of-war. Even from Earth, we are surrounded by this invisible universe. Every galaxy, every cluster, every filament we can see is embedded in dark matter. Every accelerating galaxy is being pushed by dark energy. Our measurements, telescopes, and surveys are just tools to make the invisible visible. They allow us to map the unseen, quantify forces we cannot feel, and understand the rules of the cosmic stage that we live on. Dark matter and dark energy are not just abstract ideas. They are the hidden backbone of reality, influencing the universe on every scale. From the tiniest dwarf galaxy, barely clinging together, to the vast cosmic web connecting billions of light years, these invisible forces define the motion, structure, and expansion of everything. Observing galaxies, measuring redshifts, detecting lensing patterns, and mapping cosmic structure all reveal this unseen realm, showing that the universe is far stranger and more complex than what our eyes can perceive. Picture this. We start on Earth, standing under a night sky, looking up at the stars. Every point of light seems close, intimate, and familiar. A firefly hovering, a distant twinkle in the darkness, a reflection of our own human curiosity. But then, as if pulled backward by an invisible zoom lens, we leave our backyard, our city, our planet, and we begin to drift outward, past the Moon, past Mars, past Jupiter. The solar system shrinks into a tiny dot, the Sun a flicker among countless others. The Milky Way stretches before us like a glowing ribbon, a river of stars spiraling through the darkness, with its billions of suns and planets held together by gravity, moving in a silent, elegant dance. Beyond that, the local group of galaxies floats, interacting in subtle tugs and pushes, forming clusters and chains. And beyond even that, the superclusters, the filaments, and the cosmic web spread like a glowing lattice across unimaginable distances. Space itself stretches, carrying everything outward, galaxies receding, some faster than the speed of light, not because they are moving in the traditional sense, but because space between them is growing. This is the universe as science allows us to see it. What we measure, what we map, what we understand, all comes from careful observation, meticulous measurement, and relentless curiosity. Telescopes like Hubble and the James Webb Space Telescope let us peer back billions of years, capturing light that began its journey before Earth even existed. Surveys like SDSS trace millions of galaxies, mapping the cosmic web with astonishing precision. Redshifts, standard candles, and baryon acoustic oscillations act as our rulers, letting us translate the dance of photons into distances, motion, and history. Gravitational lensing, subtle ripples in space-time, reveal hidden matter, showing us structures invisible to the naked eye. Every technique, every measurement is a testament to human ingenuity. We can't touch dark matter or dark energy, yet their presence is clear in how galaxies spin, how the universe expands, and how light bends around unseen mass. We cannot see beyond the cosmic horizon, yet we understand what lies within it with remarkable precision, constructing models of structure, motion, and evolution from the faintest signals across the electromagnetic spectrum. Science gives us tools to explore the unseen, to measure what is invisible, and to push the boundaries of knowledge without leaving Earth. Even the concept of infinity is no longer just abstract philosophy. Observational science confronts it carefully. The observable universe is a bubble, a limit defined by how far light has traveled since the Big Bang, about 13.8 billion years ago. Beyond that bubble may lie more universe, perhaps infinite space, perhaps structures too distant ever to reach. While we cannot measure beyond the horizon, we can measure within it with extraordinary detail, from individual stars to the filaments of the cosmic web, and from the first light of the cosmic microwave background to the accelerating expansion of space. Our cosmic maps are not complete, but they are precise within the limits of what we can see, offering a glimpse of the grand design, the invisible scaffolding, and the ongoing evolution of the cosmos. As we zoom back inward toward Earth, the scale shifts once more. All the vast distances, the unseen mass, the accelerating expansion, suddenly human life is still here, on a small spinning planet, orbiting a star in a galaxy among billions. Yet, Our ability to observe, measure, and understand connects us to this enormity. When we look at the sky, we are not just seeing lights. We are seeing billions of years of history. We are tracing the movements of matter shaped by invisible forces. We are witnessing the ongoing story of the universe itself. Science bridges the gap between human scale and cosmic scale, giving meaning to our place in space without shrinking the mystery or the wonder. The cinematic journey from backyard to cosmic web emphasizes this human connection. By measuring, mapping, and observing, we take part in a grand adventure. Telescopes become our eyes across space and time. Particle detectors and underground labs extend our reach into the invisible. Simulations let us experiment with universes that exist only in code to understand the rules that govern our own. Every photon captured, every supernova catalogued, every distortion mapped in gravitational lensing is a piece of the puzzle. Each contributes to a living picture of the universe, revealing patterns, forces, and processes that operate on scales far beyond anything we experience directly. The universe is vast, perhaps even infinite, but the human mind can comprehend it in meaningful ways through careful science. Observational limits like the cosmic horizon do not frustrate discovery. They define the frontier, guiding where we look next and challenging us to build better instruments, design more sensitive detectors, and refine our models. In studying the universe, we are not only uncovering distant galaxies, dark matter, or the subtle push of dark energy, we are measuring reality itself, piecing together a story billions of years in the making. What makes this cosmic perspective so awe-inspiring is that our understanding is growing continuously. New telescopes like the Rubin Observatory and the Euclid mission will scan the skies in unprecedented detail, tracking billions of galaxies and mapping the distribution of dark matter with incredible resolution. Future gravitational wave detectors will let us hear the universe in ways never before possible, tracing the ripples of cosmic events across space and time. Particle physics experiments continue to hunt for the particles that make up dark matter. Each discovery refines our measurements, sharpens our models, and extends the boundaries of what we can observe. Science is also iterative, precise, and humble. It does not assume what it cannot measure. It does not speculate beyond the evidence, and yet, within what can be observed, the cosmos is mind-bogglingly complex, elegant, and immense. Every galaxy, every cluster, every filament, and every void fits into a structure that obeys laws, patterns, and interactions detectable by human ingenuity. By tracing the cosmic web, measuring expansion, and observing the motion of matter, we connect Earth to the universe, placing our tiny planet within a narrative that spans billions of light years. Zooming back from the cosmic web to our local group, from the Milky Way to the solar system, from the Sun to Earth, the perspective is clear. Our planet is small, yet our understanding is immense. Each observation, each measurement, each experiment is a window into a universe far larger than ourselves. The stars, galaxies, and filaments we see, and the dark matter and dark energy we detect, shows reality is bigger, stranger, and more beautiful than anything we can touch or imagine.